everyone. We have 5 minutes delay. Sorry for that. So today, entire day will be discussed on network on chip, its security, and then its mitigation. And the entire day will be taken by this.
Good morning. We are going to talk about network on chip security. So, the first half will only talk about the security and design for security solutions, and in the second half we will talk about how do we use machine learning to basically kind of mount attack on some of those security primitives or kind of detect some of the security vulnerabilities. So, it is a lot of techniques I am going to talk about, there are many more. But the key idea is, if you recall our earlier discussion, whenever we talk about security, first question we ask, if we already know there are so many vulnerabilities, why did not they design certain mechanisms so that these security attacks will not happen. So, that is why the first part of the talk I am going to talk about what are the designs out there or researchers have done that is designed to make it secure. Right. So, think about the words encryption, authentication and all that stuff. In the context of network on chip, there will be few more I will introduce. But before I begin there, any devices you look at, whether the form factor is small or form factor is big, whether it is a car, airplane, your phone, gadgets, the core brain inside is a system on chip. Even in your phone there is at least one system on chip, there could be many. And when you open that system on chip and zoom inside and pull it up, what you are going to see conceptually something like this. Of course, they are not placed at the boundary, just for picturization I am showing. So, you are going to have memory, processor, DAC, digital to analog converter, analog to digital converter, FPGA, controllers, graphics processing unit, and it is not just one of each. In the next slide I will show you, even the processor, there could be hundreds of processors inside that single chip. So, today's talk is about how do these people talk to each other. What is this communication fabric? Before you understand this, you have to understand how is all these computers talking to each other. How is the cell phones connecting to the tower? That is a network. The cell phone talking to the cell phone tower. When you call your let us say your friend in Switzerland, then it talks to whatever nearby cell phone tower. From that tower it might go to the satellite, from that satellite it might go to the satellite in the Switzerland side, that goes to a cell phone tower, then that the signals go to the cell phone and that receives it. That is a network. You may not see it, it may not feel like, or you can think of bunch of computers that is connected here to the IIT Guwahati network. It might be kind of normal copper wires or it could be optical fiber. Those are the physical wires somewhere, optical fiber or copper wires laid down in these buildings. For example, right there you can see this all these cords going in. This is a network. Some of them are local area network, like the things you see in this room. Some of them are global area network, like the network that is all these departments, computer and all this connected. And people might make a hotspot with Wi-Fi, just all of your devices connected, that is also a network. And this Wi-Fi hotspot network might connect to this network, might connect to wireless network, but they have to somehow connect in some manner. Same analogy we are applying in a restrictive environment. So, before I go any further, the first question I want to ask, that is the question I asked, right question I asked about 10-15 years ago to myself. There are all these solutions already exist in the local area network, global area network, wireless network community. Why should I do research on this area? Why can't I just take those solutions and implement it here? I want to hear your thoughts. Why can't I just take those solutions and put it in here? Or if I am in the company, I already know the solution, how encryption works, how authentication works, I exactly know the primitives, cryptographic libraries, I know everything, I just implement it. What is the problem? Even before that I will ask the question, why did I do research in that area in the first place? There is nothing new to be done, everything is understood, well known, why would you do it? That question I will answer. because the network on chip even today, even after 10 years of research, it does not implement any security primitives here, most companies do not. The assumption is, remember what is the assumption of thread model? Assumption is these communications are not assumed, are assumed to be trustworthy. In fact, I forgot to mention in the trusted execution environment definition, when they talk about, let me just do draw two cores here. Let me just draw two of them. Let us say this is core 1, this is core 2, and then these two core are talking to some folks here and there. This idea of this core 2 talking through this path in trusted execution environment definition, that is not even assumed to be a problem. Problem is the application talking to each other, are they accessing the pages right. So, when memory is involved, antenna is getting on, memory, page, somebody accessing my location, but this traffic C1, this might be in the enclave, this traffic going through it, somebody else's traffic going through this path during this bus communication. I will show what that exact communication is. The assumption is a bunch of zeros and ones are flowing through this way, bunch of zeros and ones are flowing through this way, they do not have any computing ability, they are like water flowing through, or whatever may be the assumption, there is no attack surface. So, even trusted execution, if you open it up, that document does not even talk about this as a potential vulnerability. So, those things were not implemented and that bothered me, I started. Now, I ask the next question, even if you start research, it is the solutions exist. We exactly know two parties wants to talk, just encrypt the message and done. What is the difference in layman terms? Yes.
So, probably because the conventional protocols that we have a higher overhead, and that kind of overhead we can't take on a SOC.
Absolutely. You should guess 20 out of 20 or 50 out of 50 in that exam. The idea is those have no resource constraint. Let us say your computer talking to another computer, those are connected to the power supply or battery, whatever it is. It can take computational complexity, amount of battery power or power it takes, it does not matter. Probably it does, even there people are trying to come up with, but here it is a resource constraint, lot of resources, it is not necessarily just power. Even the point to point communication, whether it should happen in 2 millisecond, 2 nanosecond, there is a tight bound, but there is an advantage. This is not like in normal domain, the network should work even if like right now there are 16-20 people here. If there are 200 people here, network still should work. So, you kind of design it like 200 people can connect computer, 500 can connect, here you kind of know. It is still in the order of 100, in an automotive SOC typically have about 200 to 300 components, but it is not like thousands or millions. It is not like in the cloud nobody knows how many computers are connected and you need to deal with their communication. So, we do not have that story. So, it is kind of a application specific. So, you can take that advantage, customize for it, but that is also become a disadvantage because it is a resource constraint. You do not have unlimited time to compute that highly accurate, really security robust solution. So, that is why I took a deep look, should we have any solution at all or we just let it go the way it is. So, I am going to just talk about those issues, but before I go there, I promised that I will show you that the number of cores or even the processor core. Remember, it has lot of component, even any of the component you look at, they are also in the order of hundreds, whether 128. So, right now we have 128 around 180 cores, whatever it is, there are those many processors. Now, every SOC may not have those many cores, some may have 4, 8, some may have more, but you need to talk about connectivity. In the past 20 years ago, bus used to be de facto solution. In fact, when I talked about security engine, bus is used as the solution. When you are putting 5, 10, maybe 16 components, it would be fine. In fact, there were cases where many designs would have everybody to everybody connection. So, which used to be fine in 20 years. But later it becomes a problem when you are putting so many components on the same bus. If you are putting let us say 16 of them, then 16 even if they are sending 32 bit data per clock cycle, 16 multiplied by 32, your bus size has to be that big, or they need to do time multiplex or bus arbitration logic. Either way, that is not a scalable solution. You cannot go 16, maybe you can still accommodate 32, 64, 128, it is not going to work, everybody will slow down. So, then this is also not a solution, you put just somebody and try to do from many reasons. So, the cost, remember inside the chip there is no soccer field there. So, that free space you can just draw whatever you want to draw, it is all restricted, and any line trying to cross any line, parasite effect and all that, first the cost of area, communication overhead. So, it is not even feasible when number of nodes are really large. So, then there are a lot of solutions came in, but this one I already showed you. So, the supply chain vulnerability would equally affect, earlier we talked about affecting cryptographic module, affecting computing nodes, even the network on chip is also an IP, that also will affect. So, the bottom line is, if you look at any system on chip, it would, or any device for that matter, it would have some computing nodes, some for storage, which is think of processor, think of memory, and some for communication. In today's discussion, we are going to focus on communication, and there is a lot of research on securing computation, securing storage and computation from different abstraction level, right. You can design secure hardware or cryptographic module, you can do secure compilation like Dr. Karfa does, you can do secure synthesis, all of those focus on computation. You can do secure storage devices and non-volatile and all that, there is a lot of technology at different layers. So, communication, there has been very little work on the SOC space when I started, now there is a lot of work. And another reason, the motivation factor for me was when I started thinking, if an attacker can get access to that communication, which is hard by the way, it is not that easy, you just get into somebody else's chip in the communication you can observe, but if you can, everybody is talking through that communication fabric. Even if it is encrypted, you can still figure out something. Let me ask this question before I go further. So, if let us talk about just processor and memory, let us not complicate it, processor and memory talking, right, and it is all encrypted data, all encrypted data. My hypothesis is somebody sitting here can still mount an attack if they can observe this bus. Can any of you tell me what attack can I do? It is all encrypted data, and assumption is you will not be able to find the key, you do not know the key. Good encryption, no side channel, nothing. What attack can I do?
Man in the middle or eavesdropping.
Eavesdropping, so what signals are going through, I am talking to Dr. Karfa on the phone, you eavesdrop on those signals, it is all encrypted signal, you do not know what we are talking unless you are listening right there. So, eavesdropping is not going to help here. What kind of attack you can do where you can find something out of it? Actually, you can do lot of type of attack, let me tell you the simplest one. So, for example, by observing this I can figure out what application you are running with little knowledge. I know you are running a sorting algorithm, all I have to figure out, is it bubble sort, is it for example insertion sort, and each of those bubble sort will have 2 for loop, insertion something, all I need to figure out that loop, but how do I figure out from the encrypted data? Remember the data is encrypted, address is not. Data is encrypted, address is not. That is why I exactly know where processor is requesting, and when what the data coming back after load, that I do not know, that is encrypted, but the address is going to is not encrypted. And in fact, you will see this problem even in network on chip, that the header is not encrypted, because if you encrypt the header, the problem is whoever is receiving and trying to figure out whom to send, they need to decrypt and figure out, that is going to slow down everything. Header is not encrypted, it is just the message is encrypted. So, your email you want to send is broken down into pieces called fleets, every fleet will have header bit, this bit, control bit, authentication bit, the message authentication identifier, all that. So, data is encrypted, but the header part, minimal part, that is not encrypted. Either way, once you know that, then you are basically seeing that access to a location is 10 times, then followed by something, then followed by something, and this story, these addresses are repeating 20 times, and then there are 2 loops of some addresses, you would be able to construct the structure, and from that structure you will be able to figure out whether it is insertion sort or bubble sort. There are many mitigations for that, but I simply wanted to say, when your brain is saying, well, I know it is encryption, therefore, it is all safe, think again. whether any other type of attack you can do. Again, if you did not know whether it is a sorting algorithm, you did not know anything about anything, for you to figure, even you might have got some structure, but are you going to take that structure and try to figure out all the algorithms in the world that is available and whether it matches with anybody else? That is not going to be feasible, right. So, that is why security attacks are always in steps. You know a little bit, you talk to somebody, get little bit information, then use that to talk to somebody else, and then you mount the attack. Any questions on this? So, the key idea is, when I started, is if somebody have access to the network, they pretty much get all the information. So, it works both ways. If I can implement a security primitive in the network, I can protect lot of stuff, I have a better visibility if I am a defender. If I am an attacker, I have a undue advantage, it is a focal point. So, now this security story is challenging compared to actually even normal network, because first of all, this is a source, this is a destination, they want to talk, I still did not say how they are connected, but no matter how they are connected, at least in our research we considered 3 technology, there are few more, so that you know, but 3 major one, and this one most of you are aware of, electrical. The wiring, that the wiring all you have, you send high or low or 5 volt or 0 volt or stuff like that, twisted wire, and I do not want to get to the details of discussion, but electrical wire communicates all that information once you make the packet, then all that stuff. But what you might not be aware of is, this also you might be aware of, because most of the networks these days you know or you do not know, even below the ocean, those are all optical fiber network. It is based on lights, lights are traveling. So, you convert the data into light, and from that light again you convert back data. So, they have a lot of serious advantages, and some of the attacks on optical fiber is basically you try to bend, you shake the ground in some way, and you can do some distortion, but it is much more robust than electrical. Think of a glass tube, literally you are throwing light through it, that is how it is, but whatever it is, that is the optical NOC. It is not very popular. Are there SOC prototypes? Yes, but it is not as prevalent as there for the network on chip. But in real world, actually there are more optical networks, or if you look at total amount of data traveling in the world, most of them are traveling through optical network as of today. When you are getting all these high speed internet, Wi-Fi at home, it is only possible because of optical network. So, optical network is kind of very common in the classical computer communication network, but it is very rare as of today in the network on chip. And then there is a in between, which is wireless, of course, is pretty much everything is wireless in classical computer network story, right. And it is somewhere in the middle, there is not too many prototypes, most of the computers and things you buy, those are in electrical NOC, but there are wireless NOC, where the idea is you have all these components, I have details later, and you have, earlier I used to call them micro antennas, now they are nano antennas, nano dimensions of antennas, but it has exact same property. Next to your house, if you have seen all these big tower, those are radio frequency communication. These components understand and receive, think of each of them is a cell phone, think of it. They understand those communication, and you still have to deal with all these problems, the interference, right. To understand that, think about there is a tower here and then there is a big gathering, 100,000, 200,000 people in a field, maybe convocation day, that day talking would be really problematic, not because everybody making noise, because it is tower and congestion, RF. But if there is a tower, 100,000 people sparsed around the thing, it is not a problem. Here tiny place, all these antenna, and that kind of story is a problem. Nonetheless, the point I wanted to get across, there are a lot of ways these people can communicate, and most of the solution today, even the wireless one, they are hybrid. That means everybody does not have wireless communication capability. So, they have, there is a electrical as well as there is wireless, and I will show you that hybrid topology, where, or let me just draw one of them just to get an idea. Let us say it is a 4x4, 16 components connected in a mesh, and let us say this one has a tower, and maybe just for fun this one has tower, it does not make sense. So, then if this is source and this one is destination. The electrical would have been, let me use the red color, electrical could have been this way, or it can come like this to this wireless tower, this wireless to this wireless it comes, and then from here to here electrical. Now, in this one it seems like direct electrical would have been just good enough. Why do I go to the little electrical? So, this is similar to, this is your highway. Before you get to your highway, you do little bit of local city kind of drive, then you go to the highway and then you get out of the highway. So, that kind of hybrid model also exists, and that is all the most of the prototypes that exist in the wireless, they are of this kind, and there are not too many of them. Any questions? Yes, please.
What are the advantages of going wireless or optical?
So, actually the optical or wireless has this problem of you need to wire them, that connectivity, that wiring, that space, all of that problem is gone in wireless, that is one. Then there is a second advantage, electrical would be, electrical wireless is say multi hop. So, you want to go to S to D, it is 1 hop, 2 hop, 3 hop, 4 hop, 5 hop. You have to go via some other people, right. In this hybrid, of course, you still have 1, 2, 3, 4, but in general if everybody has a communication, it is a single hop communication. Even in your cell phone, I do not think it is a single hop for anybody, right. When two of the people are talking, it still go to the at least a tower, at least 2 hop, but nonetheless that is the key idea. You reduce the number of hop, but it introduces its disadvantages, all these RF interference and all that stuff. Any other questions? That is a very good question, right. Now, there are lot of there are many other things to deal with when you want to talk about network on chip security, which is like any other design principle, you have this eternal trade off. Do I be honest? Do I make lot more money? No, I am joking. So, you have earlier you had performance, energy and area trade off, now you also have a security one, and by the way this story is also true for classical computer networks. If you want to implement a very secure algorithm, it is going to take a lot of energy, it is going to slow down your performance little bit. Like a typical AES, even the smallest counter mode, it would take somewhere around 32 cycles. So, earlier you are executing one instruction every clock cycle, now you have encryption, you have to wait for 32 cycles. Whoever want to use the result of that has to wait for 32 cycles. Load instruction, we already have a problem, cache may be miss or hit, now cache controller is encrypting it, even if it is a cache hit, it is going to take 32 plus 1 cycle, 33 cycles. So, every cache hit it is 33 cycles, that is too much of performance penalty. Do I want it to be secure to avoid somebody eavesdropping, or do I want to be fast? Then there is a middle ground which I will talk about, which I do not want the highest level of security, I will settle for a little lower, but I do not want to, I do not want to do anything kind of story. I want to do something, but I will not go that far. Any other questions? So, if you think about it and look at it, today there are many solutions, and today I am going to talk about mostly a solution that is mesh based, but there are many more and each has its own research challenges. So, in mesh based solution, the key idea is you have lot of components and they are, so for example, this one 4 cross 4, there are 16 components, think of 16 processor cores, they are connected exactly this way. So, if the source, want to talk to destination, then it goes through each of the nodes. Even cell phone world, there was this idea of peer to peer communication. So, instead of if two of you are talking either to yourself or somebody, should it go multiple people talking, should it go to the tower and come back, or should your phone use the another phone nearby its range or Wi-Fi range and actually travel through that. Now, you might think that model is actually popular in many countries, peer to peer communication, and the way it is kind of a reward system. Why would I use your phone call to be routed through my phone? The way I use, then the company gives you data, gives you your free whatever monthly subscription, it becomes free or half. So, then there is some understanding of that nature, but whatever it is, here it is basically peer to peer. For this information need to route, it need to go through other nodes in the network. Remember, those folks are also talking to other people. So, we will zoom in to see how all these happens. But before I go any further, when I try to do network on chip secure, we are still addressing exactly same problems we addressed in any other network, which is authentication, who is talking to me. We are talking about data integrity, did anybody modify the data when the communication going on, did anybody I do not want anybody to know what I am talking. And let me start with the first one, anonymous routing. So, what does the word anonymous means to you? Anonymous basically means if I am talking to somebody, it is okay, you understand I am talking, I do not want you to know whom am I talking to, I do not want you to know who is my girlfriend and boyfriend, I do not want you to know, it is okay, you know I have somebody, so that I can boost my chest, it is okay. But the question then attack is, how do I break that anonymity, how do I figure out whom you are talking to? Are you talking to my girlfriend? Then I have a serious problem, right, I need to know and break that. Right, most friend circle, that is how they break this whole not understanding the line, that there is a line between even friends. So, this is a source and destination talking, in between there is a node, malicious node which is listening. Now, this is where the threat model starts, this is where supply chain vulnerability comes into picture. If you do not believe this threat model is possible, then you should not pursue this line of research, which is one of the node. In fact, it is not the node that is malicious. Remember, each of the node I zoomed in, it has three parts. One part is the IP itself, let us say this is the processor, this is the CPU. In addition to that, you have the shared resources and the router. The shared resources typically is network, for example, it is the network interface card. Think of glue logic, whichever way you feel comfortable. So, this was the network interface and this is the router. Router is the one who maintains who is talking to whom. Remember, this processor is computing whatever program it is supposed to compute, but the router and remember this router, if there is information coming for this processor, this router will forward to itself. So, a better picture would be, think of, I have few other pictures. So, think of this as a network interface and router, and then there is a IP, the CPU is hanging from here, that would be a better picture. Everybody has the computing core and network interface and router. Router, think of, for the time being, think of a lookup table. A request comes in, a address comes in, you try to figure out where does it go, and if it is a XY protocol, then you go in X direction as much as possible, then you go in Y direction, but that algorithm is orthogonal. Any questions on this structure? So, the threat model is there is somebody in the middle sitting and trying to understand who is talking to whom. So, the objective of this one and what we will try to present, how do I stop that, they are figuring it out. So, basically they are tracing packet, they are doing different kind of analysis to figure out who is talking to whom. Now, before I introduce, you guys have no allergy on onions or garlic, right? So, I am going to introduce the solutions that exist in computer networks community, and it is called onion routing. I did not invent it. So, onion routing, basically idea is same. Let me go back to the previous slide and show you what onion routing looks like here. So, the way onion routing works, so let us say let us choose the same one, source wants to talk to destination, and there are multiple people, let us give them name A is already given. So, let us call it B, C, E, these are the nodes. For A to send a message to D, here is the message, see how onion forms. First of all, the message need to be encrypted with the key of whom? ideal situation it should be D, but in a onion routing the lowest layer is always the key for D. Then you add another layer that was for key for E, with key of E, public key of E, then another layer, I think very quickly I will go out of space, then key of C, then I am just drawing this part, then key of A, then key of B, that is the onion I form. So, you are encrypting this message with the key of D, that is exactly normally we do. Whoever you are sending, take their public key, encrypt it. In the onion routing, which path is traveling, if you know the XY routing, you exactly know which path it travels, then you know who are the components it is going to go through, and everybody has access to everybody else's public key, and you basically encrypt that message with those public keys, right. And then you send this one to the B. Can anybody help me, when it goes to B, what happens? B decrypts it using its own private key, and that would result in this layer would be gone. It will be able to open only the outermost layer of the onion. Then that one goes to A is malicious in this case, but all A has the ability to open it. A does not know what is the message, because this layer A cannot open unless it has the unless it is able to compromise C and found the private key of C, right. So, that happens, and then it goes to C, C opens this layer, then it goes to E, E opens this layer, then it goes to D, D is the only one who can open this layer and then know the message of M. This has huge overhead. You have to do so many encryption, packet and message becomes larger, although pictorially I drawn it, in reality it is still bunch of bits, right. Even after encryption, the good part of encryption is the size does not change, unlike compression, size reduces or decompress you become, in compression size remains same. Anybody knows what happens to the compressed data? One dictionary word, it become randomized. If it is a perfect encryption technique, it become perfectly set of random bits. If you can compute the entropy and figure out this perfectly random set of bits. If it is not a good encryption algorithm, because when things are random, applying any form of attack, any kind of thing does not work, that is the key idea, but either way. So, is the idea clear what is anonymous routing and why onion routing would be really expensive? Okay. Now that, so for the first attack and solution I am taking little extra time, but subsequent one will go faster, because then all we talk about the solution, not all these details how they travel, right. Any question on this one? Now, anybody, so onion routing we talked about, like layer after layer. Anybody knows what is the garlic routing then? What is the difference between onion and garlic? Nobody knows? Onion has this, yes, go ahead please. Onion has the story of layer after layer after layer. Garlic also has layer, but in addition to this layer, let me use a different color, so it would be interesting. It has this, what is it called, cloves. This has all these cloves, they have their own layer, but the interesting part is, let me try one more. They have their layer, in addition there would be some outer layer. In addition there would be some outer layer. So, that is basically the garlic. Can anybody then connect how garlic communication will happen in my previous example? Onion I said you just encrypt for each of the people in the route, and how would garlic communication will happen?
You can add a VPN on top of this.
Yes and no. So, this one garlic communication, assume you are not sending for one party, you are sending for multiple parties, and where it happens, if you took computer architecture course, like when you have invalidation messages. If a cache is trying to write in a multi-core scenario, cache is trying to write into its cache and other people may have a copy of that data in their local cache, you send invalidation messages. So, there are many such scenario, you send the same message to a lot of people, then you can do this. Even if you are sending different messages, let me create a scenario. Let us say here are the kind of nodes. So, let us say this one is trying to, let me use a different color. This one is trying to talk to this one, and then this one is trying to talk to this one and all that stuff. Then you can see at least for certain part of the story we could create garlic. So, this message is for the clove, one of the clove, this message is for another clove, and that actually have a higher security strength. And but there are many, invalidation is one perfect example. Any kind of multicast communication, instead of treating every request as a independent, because if lot of people are trying to go to, let us say from here to the airport, and from different halls they are coming with their cycle or whatever they can come, but somewhere there is a bus pickup place that will go to the airport. So, at least that part of the journey they are together, that is the idea of garlic. And right. So, basically it does not, it is coming from multiple sources, then you form the garlic propagates, again it can go to different destination. Now, all of the solutions actually existed in traditional computer networks. We borrowed those ideas and make them lightweight, that is basically the key idea. And the details are not important, and this is for understanding that you have to read that 2-page or 3-page paper of Samir's secret sharing, how you can use a Lagrange basically coefficients in a polynomial. And this is for the first time I realized why they taught Lagrange and all these Laplace. Laplace at least I understood, because when you do electrical whatever circuits design and all that, you have 1 over S and all that. Lagrange I never used, and I always wondered why in engineering mathematics they teach these things, nobody will ever use. And this is the first time I used, 40 years later I realized, oh, that is why they teach them. But anyway, so the idea is very interesting. So, if you take points on the curve, and that is how our solution actually work. If you take points on that Lagrange polynomial, and unless the attacker, whoever that the malicious person is, it can compromise all the nodes in the path, it will not be able to figure out the message. Onion routing explicitly do this. Think of conceptually each point is an encryption, but here it is literally a point. Remember elliptic curve cryptography, it is a point on the curve, it is literally a point on the curve. It is actually not you are doing encryption of the whole message. It literally you choose points from that curve and use those points, somehow encode it in the message, put that in the message, not explicitly encoding, that will work. So, anyway, so then basically that is how it works. And if you want to see the math, how actually it works, we have the full math, but I am not going to go through all these math, how exactly this may look complicated, but it is basically saying which is one time pad, what is the message, how you OR it, how many bits of it, it is the exact details how it is. And let me see if the animation work. So, if S is trying to talk to D, it is basically, oh, this circle should have been here. It basically it is going to the router of the next one, and then that router basically trying to check, and then so on and so forth. So, the key idea is everybody knows only the previous where it is coming from and where it is going to next, that is the catch. One point in the polynomial only it knows who is my predecessor, who is my successor, it does not know anything else. It does not know. So, unless so you can still anonymous you can break if this one knows where it is coming, where it is, unless this is the source, this is the destination, then by default it is broken. But if the predecessor and successor are not the source and destination, you can never figure out based on this formulation, because there is no option for you to ask, can you tell me who was the predecessor, where it came from, you cannot ask that question in Lagrange polynomial. So, that is basically the one. So, nobody knows where else it is, and just I am showing some results quickly. So, basically anytime you do network on chip research, first thing you have, or any architecture research for that matter, these days GEM5 is kind of the de facto simulator you use. Most security attacks people do not like results from GEM5 simulator, people want you to do on the actual computer, Now it is possible. Earlier dumping data from the NOC was not even possible. There is no way you can dump data from a NOC that is on your computer. Now some of the latest servers, there is the ability, if you might be able to do that. First of all, that processor should have NOC enabled, network on chip, right, and some of the latest processor and server grade processor, they have the NOC and the ability for you to download. But all these years, early days, there was a processor called simple scaler, people used to do work in those, but now it is a processor of GEM5. Think of this is the computer architecture simulator. This comes with hook to many other softwares and simulators, and that allows you to kind of simulate the mesh, whatever network you can choose. You can run synthetic benchmark, you can run real benchmark. So, basically if you have, let us say you are modeling a 2 by 2 core, you can tell on this core I want to run a bubble sort, on this one while an insertion sort, this and that. So, then real traffic will flow, then you do not force, oh this is my source, this is my destination, whoever is talking to whom, wherever the, now question is, if bubble sort is running here, insertion sorting running here, why would they talk to each other? Any thoughts? Why on earth, if a processor is running a program, why would it talk to another processor who is running another program, totally different program? Why would they do that? Sorry? Working with same data typically will work, but that your argument will work when you are kind of parallelized, a program you parallelized into thread. Let us say you are adding 100 numbers, you divided 50 getting added here, 50 getting added here, that still do not talk, but one of them or both of them has to send it to somebody, maybe this one sends, then you add the last 2 numbers here, there is a talking. Most of the other time talking is one of them is running program, but the one I did not talk about, they also need to have a node where the memory is sitting, memory, cache and all these modules are sitting. Now, I am not talking about the local cache, the shared cache, main memory. So, everybody while they are talking, they need to go to main memory. In fact, later you will see the denial of service attack is somebody is going to spam lot of requests to this memory, knowing memory is the bottleneck, let us just overload it, so that when legitimate load store request goes in, it cannot get served. There are many scenarios while people talk, either it is a multiple threads of the same program, then natural data sharing as you said, or how the memory is placed. And remember, memory may not be placed in one place, this could be implementing a distributed multi-core architecture, where memory is also divided into multiple pieces. Then they have distributed directory, distributed memory and different pieces of memory. Typically memories are connected in the outer layer of the node for obvious reason, but whoever it is, people or a node will talk to another node for legitimate reasons, right. So, therefore, the two things that is important. So, one thing is most people spend 3 to 6 months learning the GEM5 simulator itself, GEM5 how it hooks to different kind of routing protocol and all that stuff. Then the next thing they do, two things are important in research, is the average packet latency. Of course, who is talking to whom, that would determine the delay, right, but the average packet latency, say everybody is talking to everybody in that scenario. What is a time you send a request, on an average how much time it takes for it to reach there. Remember, there are a lot of things I am not going to talk about, which is what protocol is it XY protocol and all that, number 1. Number 2, if a packet does not get delivered for whatever reason, there would be a the reminder come in, that would be a message, and would it retry after 10 millisecond if the acknowledgement does not come in. There are in the protocol itself all these embedded. I am not just talking about it. The way I am talking, as if you just take a packet, message, packetize it, send it, other party will get it for sure, but in reality that does not happen. Even if you packetize it, because of some congestion aware routing, they may go through different paths. Some of the packets may reach on email divided into, let us say, hundreds of packets. Some of the packets will reach, the remaining packet may not reach. So, it has to be resent, then in the destination it will be composed, then you see the email, all this stuff happens. That is why when you are spamming email, just think about it, think about, humanize these networks and computers and think about, I do not want to give this much of pain to that person, just do not do that. Like when you forwarding all this spam stuff from your social thing, just think about these computing nodes, what they are doing, packetting, dividing, header, encryption, onion, garlic, spices, curry, rice. Have some respect for them. Okay. So, one is the average packet latency, second thing is execution time. Here I am showing normalized execution time, whoever is worst call it 1 and but we can plot. So, what is the execution time end to end and how long does it take? Typically this is supposed to reflect on this, if average packet latency is improved, your execution time is supposed to improve, but those are the stuff. But anyway, I am just going to show some results. So, this is no anonymous routing, basically normal computation, which is the NOCs today, and then we have the anonymous routing. If you use the existing garlic or onion, it is going to take a significant amount of delay would be too bad, execution time would be too high. In contrast, if you use the Lagrange polynomial based hour implementation, then it is going to be really small. And in terms of improvement, let me see, I have number. Let me delete some of the space here. So, basically the overhead of our implementation is about 18%. If that is acceptable, that is good, but if we use the existing, it is going to have about 70% overhead. In the execution time, a similar reflection. So, I am going to talk about one more idea before the break. Any question on anonymous routing, and the next one I will just focus on just that work, we will not get into the details of this. Yes, please.
Based on the architecture, the grid based P2P communication which was shown, sir, like in the conventional we have various methods to overcome collisions, CSMA, CD and all. In this, how are we mitigating collisions?
So, first of all, when we discuss in the network community, there is a common understanding. When you are talking in application layer, do not ask question on physical layer and network layer and all that. So, in this particular scenario, it also has a very simplified bus contention mechanism. This router, and each of the router has the story of how many requests came in and who have the priority, whom should I forward first. Everybody is getting so many messages from so many places, which one should I route, do they have a priority. So, there is a miniature, all that stuff you said, there is a miniaturized version of everything implemented as of today in the real NOC devices, it is actually implemented. So, when we work, we do not worry about it, we do not talk about it. The next one I am going to talk about is the incremental encryption. And so, the idea is when the two people S and D wants to talk, so packet get encrypted and then the encrypted data goes through and packet get decrypted, and remember, so each of the module that is there, it has a router, network interface and actual component itself, it could be processor, it could be memory. Here a processor is sending a data or processor is requesting a data, right. So, in this story, if there is some man in the middle, man or woman in the middle, they will not be successful because in the communication it is a encrypted data. But the problem is the overhead is too much. If you want to implement traditional encryption, we talked about all these stuff, AES, counter, gallows mode, then we talked about elliptic curve cryptography and so much. So, RSA, it would be too expensive to implement. The delay would be too much, execution time would be too much. It is unacceptable, right, because you are sending a load request. Earlier what did you think? We send a load request, it is in cache, it takes one cycle. Dr. Karfa asked, why does it take more than that, right? Because of all these stuff goes on, then your delay becomes much higher. Because in simplified model we assume wherever the processor is, cache is the local cache is connected, but any other cache, any other memory, shared cache, it is just all over the place, right. And then what is our insight on this? The insight is, if you look at the NOC traffic, by the way, this insight actually true even if you take the benchmark, spec benchmarks on the processor, all these 32-bit data you look at, most of the bytes are zeros. It is not just in the network traffic. And the interesting part is the email you write, the email I write are different. but at the packet level it turned out when you look at the 60, typically packet sizes are 64 bit, 64, 128, whichever you want to implement, and when you look at the data, whether there is a 64 bit data, so that like 8 bytes 1 2 3 4 1 2 3 4 5 6 7 8 bytes, it turned out that most of the bytes are 0. Actually, if it is 0 or not, it is not important for incremental encryption. 80% of them actually have only one block that has data, other data is similar. In this context, who is similar and who is different compared to the previous one. For incremental encryption, that is what we observed, that 80% of the packets have only one byte. In fact, in most of the cases it is not even one byte, only few bits different, but we still look at byte level. Can any of you give me an idea why? Why you have all these data and we have 64 bit all these packets and only few bits are different compared to previous one and the next one? Where this should happen, because it is not like 1 or 2, it is 80% of them. There has to be something obvious here we are missing. What is it? Yes, please.
The data would be less and header and padding would be more, that is why.
But header and padding, remember, it is going to different places, so they are all supposed to be different. Why would it be similar? Remember, I am saying only one block is, it is not importantly significant, only one block is different, the previous block or data that was sent, previous packet, and this packet only one block is different. Why? Where in your programming paradigm you have seen something that justifies this? You are still thinking. When you have a load instruction, think about processor and memory talking. If you have a load instruction, load to R1, right, and if you have a for loop, of course that is not how we write a program, we have only one load and repeat. Load to R1, then you have an address, this address increases by a byte number, that is it. Of course, this is a silly example I mentioned, probably the next load instruction is load R2. Technically speaking, even if this address is for one, at least 2 bytes should be different, this byte or that byte should be different, but nonetheless that is the key idea, that is the key idea, that the load, the binary for load is exactly the same, everything else is exactly the same, only thing changes is the destination register and kind of the address. And even if the address, if it is in a loop or you are going for an array, you are going for the first address, then the +4, then the +4. So, it is just changing by a byte. So, it should not be a surprise that only one block is different compared to the previous one, right. So, in fact, as I said, this observation is true even in general purpose computing. Even if you take spec benchmarks, do all these analysis, and I forgot to tell you, in architecture community, when you write paper compared to other community, you have to do lot of analysis, you have to set lot of context to show why that is relevant, who gets benefited and what is the observation. So, when if you do that analysis, you will observe about 40% of the cases everybody is 0 except the least significant byte, everything is 0, that is how its computation happens. And anyway, so when you sum it up, 80% of them have one block, 20% of the things have 2 blocks difference. So, although you have like 16 bit blocks, so there are actually 4 blocks, this is how the difference is. So, the 2 of the blocks are always the same kind of story. So, then how does this story then works? Let me just finish this. So, basically in a traditional encryption, if you are instead of 16 bit block, I just made it a small 8 bit blocks just for the illustration, or you can think of 16 bit blocks. So, if traditional encryption, you just encrypt both blocks, right, and then another set of blocks came in, you encrypt those blocks, and let us assume this case instead of 32 cycle, it is for 20 cycle it takes for encryption, and then you keep on doing for this series we need 16 clock cycle. If you want to do incremental encryption, and so by the way, I did not invent incremental encryption, there are technologies I did not talk when the cryptographic discussion I did, like Hummingbird and variations, they actually support this incremental encryption. Lightweight solution is Hummingbird. And so then you do 20 cycle, but the next time when you are looking at these data, we are observing that this particular block which I put in there just so that you can see they are actually same, right. So, they are actually same. So, I do not need to do compression on this one, I can just do compression on this one, that is basically the key idea. So, these two are same, so I do not need to do anything, but of course, these two are different. Now, if I put this data, that is why it is in purple color, we kind of see these two are same and those two are different. So, because the same one I do not have to encrypt anymore, I only encrypt, but I still have to pass some extra few bits to convey that which one I compressed, which blocks I did not compress. So, that it takes the compressed data from there, and details again you can see that is the basic idea. You save on that, and even if this one instead of taking 20, if it is kind of take your 22 cycle, because you have little bit of extra manipulation. So, then total is 42 instead of total being 60 cycles. That is the key idea of incremental encryption, and rest of the stuff I am basically going to skip. So, basically in the experimental setup it is a mesh NOC with different number of core, and as I said in networking community or network on chip community, two types of benchmarks are expected you show. One is synthetic benchmark, where you kind of randomly generate traffic with different injection rate and how quickly they kind of sending data. One is real benchmark you run on those cores, and then you show the result. So, basically in terms of network on chip delay, the compared to traditional encryption we can produce 57% improvement. In case of here it is about 10% improvement. So, we stop here, we will start at 11:30. Thank you.
Okay, so one announcement. So today we have one more session from 11 to 12:30 that I have already there, and then we have lunch here that I have told you. The only change is that although we have lunch here, but we will have break for 2 hours. So post lunch we will start again at 2:30. So I need some time for preparing some slides. So we have to go for that. So we will have lunch and you can sleep here or go to hostel, wherever you want to sleep, you sleep. But we will start at 2:30.
Good morning. In the previous lecture, we looked at in on chip network or on chip communication network, what kind of ways we can protect the anonymity of the communication. We also looked into how we can do incremental encryption, that is going to make it lightweight, yet it gives you security. Now, we are going to talk about trust aware writing. Let me just set the context. So, in reality, when you have a set of components, and this also exists in classical computer networks, some of the components are trustworthy, think of trusted execution environment, some of the components may not be trustworthy. Now, the question is, if there are two zones where things are trustworthy, how would they communicate? If I want to communicate between, if this is the source and if somebody else is the destination, I want to let us say compute from this place to this place, there is no way. वो बैटरी ये निकल गया था हाँ हाँ हेलो 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 Good morning. Today we are going to talk about trust aware routing. The threat model basically looks into the components where two parties want to talk, both of them are trustworthy, they are good people in the society, but it is just that they cannot directly talk, they have to talk through, no matter how they talk, whatever routing protocol, it needs to go through the territory where things are potentially untrusted. Then question is, how do these people communicate and keeps the communication safe, secure, authentic during the communication? Is there any way? Of course, this question is invalid if there is no possible path. If there is a path, can you find the path? In fact, the real question is which path is the least troubling. You have to go through the forest from point A to point B, which forest do you cross through and your chances of survival is highest. So, that is really the problem of trust aware routing. So, what we try to do, so this basically what solution do you kind of talk about, and low performance, and the bigger problem is in many of these cases, if you think of Trojan, if you think of something else, they may not be fully malicious all the time. If that they are fully malicious, we know by definition there is no path exists, you cannot communicate. Then somebody who is intermittently malicious, sometimes they will look blue, sometimes they will look orange. So, in that kind of situation, how and what you communicate. And there are a lot of work, as I said, in the classical computing domain, and there are also different related works, and we are trying to make it lightweight. So, the way lightweight works is basically, so when you meet with strangers, when I hire a PhD student or anything you do, you have to deal with such situation all the time. What do I do when I hire somebody, a PhD student? We send an email to the professor who taught the course, either that name I get from the application itself, or I just try to figure out which university, oh I know that university, Dr. Karfa. So, you kind of have the word of mouth and you rely on it. And so, then therefore, if I am A, I am trying to talk to B, either directly, if previously I never encountered with B, I have no clue. But if I was hurt, offended, cheated, then I know how to deal with B or whether to deal at all. What about C? For C, I never spoke with C, but B did. So, then I want to get the view of from the B or whatever the trust B says. Now, if B says, oh C is wonderful, how much do I trust B's opinion? Then you multiply by that. So, that is basically the basic idea. So, A is confident that B is trustworthy, that is like 1. Then A is confident B is malicious, that is like -1. Again the numbers you can change, that is like, and A has no idea about B, that is like 0. So, we are trying to assign some trust values, so that we try to compute in the routing protocol, we kind of do some kind of computation. So, we came up with bunch of equations following some ideas and theories, that is not important, but basically trust is updated depending on successful or unsuccessful transmission. Remember in the mesh network I talked about, when you are communicating with somebody and some packets are delivered perfectly fine, some packet came back, oh that has not been delivered, you have to retransmit. How many times you have to retransmit, but again remember you A would always send to B, but it might not be B's problem why the retransmission is happening, but still you will kind of through this equation you are going to penalize the B, because maybe somebody else in the path is actually causing the congestion, and it seems like every time I send a request, that wherever the things responded me I did not get it, you have to send it second time, third time. So, then you are kind of having little not so pleasant feeling about B. And in different types of protocol like XY protocol, XY routing protocol, you follow only one path, but in this particular story we are going to follow different paths, because if you have a fixed path you really do not have a choice, you have to send through them. So, trustworthy routing basically uses different type of path, and the key idea of all these equations is basically either it is a direct trust or it is a delegated trust. Do I believe the word and how do we propagate the trust, that is basically the one. So, destination router in same row same column, forward to neighbor along that row column towards destination, some trust values of different paths toward destination and pick the path with the largest value. So, that is the key simple idea, simple heuristic. And what you really want to then look at, so there are multiple things you look at when you are kind of evaluating. Of course, the typical thing is kind of network on chip delay and execution time, which should kind of reflect, does not need to be, and then number of packets you injected and how many of those packets actually delivered. So, when you model this and evaluate this, you have to make one of the node malicious, they are just sitting there and just destroying the packets, not forwarding it. Again what threat model you impose, here what we imposed is basically just throwing in the dustbin. A packet coming in, it is supposed to forward, it is not forwarding it, it is just throwing in the dustbin. In this kind of model, how much of performance penalty, what packet injected, and you kind of compare. So, in basically this particular work we also looked at different other comparisons with real benchmark, those were and with synthetic traffic pattern, and comparing with without malicious, if there is no malicious at all, then what should have been the performance, and with malicious and so on and so forth, and we are basically have to show that in real as well as synthetic benchmark with your solution, you if there is a path you can find such a path and your overhead is not too much, that is basically the objective, and how much less energy, area overhead, all those are important. Any question on trust aware routing, because you still have to communicate, you are trying to find a path if exists, and initially you are expected to make mistakes. The next one I am going to talk about is digital watermarking. So, you probably know what watermarking is. Here we are doing watermarking for authentication. In pictures we have watermarking and we did all of that. So, basically this watermark we are going to encoding can use packet content or timing also. How we do, you put the watermark and then it goes through the network on chip, and on the side you extract the watermark and check. Now, the question is why are you doing this watermarking? How do you do authentication normally, if you recall? Any kind of digital signature like ECDSA or which uses indirectly SHA or hashing, those are extremely expensive to implement in the network on chip. So, it basically it significantly reduces the expense of authentication. Of course, I am not going to show you the theoretical analysis which I did not show even for the incremental encryption, that when you do that how much security strength goes down. Because in block cipher, one of the classical disadvantage of block cipher, you are breaking into block and you are doing, if you think about it for a moment, if you are breaking into block and reducing the size, you cannot use 128 bit or 256 bit key anymore. It does not make sense XORing it with bunch of zeros padded. So, the moment you reduce that, then your complexity, let us say you are making 16 bit blocks and your key size is 16, 2 to the power 16, anybody can do brute force. So, that is why there are some more stuff that needs to be done for you to give some theoretical guarantee. Same thing for watermark, if you say, oh, I will use watermark for authentication, I do not want to implement elliptic curve, the digital signature algorithm, that is so expensive. But then you have to compare what was the security strength of ECDSA and what is the security strength of this. Is it easily breakable? What is the catch? You have to just say that. So, this watermarking basically idea, then the way is basically when you are sending the data, whether then any malicious component is trying to take that data out through eavesdropping, right, or it is trying to pose as somebody else. So, it is a tag based authentication, and in the tag based authentication, the way we are doing the authentication, when you are looking at different time step and the packets are going in, you are basically kind of figuring out the inter packet delay. The delay between different packets, you are trying to figure that out, and once you have the inter packet delay, then that delay itself you are encoding as a watermark, right. If you recall in the PAF, the process variation is itself you are using as a watermark. Here the inter packet delay. Now, if you are an attacker, you can always come up with a synthetic benchmark. If you know what inter packet delay got created in a particular benchmark, you can always create it. But if it is a real benchmark, every benchmark, the way packets or the inter packet delay has a unique footprint. That is what that statistics I did not show, it has a unique footprint. The delay between different packets, the way packets are going, how many sub packets are getting created, and the injection rate, propagation rate, delivery rate, if you look at, they have a unique footprint. In fact, when we talk about machine learning today in the afternoon, you will see machine learning implicitly, explicitly basically figures all this out. It is just that we did this research first, then the machine learning research. If we did not do this research, then explainable AI would have told you what it is trying to do and why it is finding certain patterns. Now, in layman terms, I wanted to break it down in layman terms, all these equations. What we are trying to do, if you look at the inter packet delay for any program, it is going to follow some form of uniform distribution. So, there would be lot of packets with hardly any delay between them, think of 0 delay. So, there would be lot of them, and then the other ones are kind of spiked out. So, which is not as beautiful as this, in reality it is kind of this. So, but it still kind of fits the kind of nice uniform distribution, right. And then what we are trying to do, so we want to shift this by certain amount. Think of you introducing some extra delay in a predictable manner, and then you shift it. So, somebody shifted is actually 1, somebody not shifted is 0. So, that is kind of the notion, and we use that as a watermark. So, once you do that, then some more equations are not important. So, then you want to do just kind of do the comparison. Again you look at, if you do that, all these stuff, shifting, delaying, how much does it affect the thing? It does. So, for example, default network on chip, and these are in, so it is like 0.4 to 0.6 or about things. So, it is like close to 20% overhead. But if you compare to the authenticated encryption, any of the authenticated encryption you already know about, then it is going to be between 40 and 1. So, it is like almost 60% overhead. So, that is the thing. If you want to implement a security mechanism, it is not going to be for free. So, you get some security, you have to pay something. As a designer, you have to make a decision, are you willing to pay that cost or not. And same thing for execution time, overall execution time for some of the benchmarks, for real benchmarks, and the execution time difference similarly, I probably summarized it. So, authentication would take 57% overhead, whereas watermarking will take only 26% overhead, and delay also have a similar kind of footprint. Any of you have any question on digital watermarking? So, if you want to pursue a research on this line, or similar to this, your core objective still remains the same. We want to enable authentication, somebody talking to somebody, can we maintain that information. Here we are maintaining that information, who is talking to somebody, or if somebody is saying I am A, this is my message to B, how do I know it is actually A. So, that signature is encoded as the inter packet delay, that is how it is. Now, we are going to introduce another concept called chaffing and winnowing for encryption, but before I do that, let us look at the threat model. So, another thing I forgot to mention, in security community, anytime you publish a paper, there has to be an explicit section on threat model. What is the threat? What is the vulnerability? What are you trying to solve? If the community or reviewer think that threat model does not sound reasonable or realistic, that sounds fake, it does not matter what you have in the paper, it is all rejected. So, here threat model is somebody, a source is trying to talk a destination, some node, right, it is trying to send the packet, and an adversary trying to eavesdrop. So, this is basically, think of an eavesdropping attack. We are trying to implement an encryption technique, but it is a lightweight encryption technique. We could have used AES, RSA, any of those, we are using a lightweight solution, right. So, adversary, so encryption will happen here, and once encrypted packet flies through, even if adversary tries to consume, it will not be able to figure out anything, because it does not have the key. Any question on this threat model? This is basically eavesdropping attack, right. So, what is the solution we are trying to do? It is motivated by seeing what happens in my village, which is when you have a set of grain, whether it is rice or paddy, whatever it is, you use the air, normal air. These days they use some fan, they have electricity. Earlier they used to use the air, and on the fan, so that the husks will, the chaff will go away, and the wheat or rice will fall down. You just separate them out. So, this is called adding, this is called chaffing, you add the garbage, and this is called winnowing, you get rid of it. So, that is the key idea, and we will do that on chip network. Any of you have the question on what is chaffing and winnowing means? Winnowing, you separate the good from bad, and chaffing is you add bad things to good things, right. So, why do you want to do that? How does that help? Before that, I want to show you an animation. So, let us say this is the message the Alice want to send to Bob, right. This is source, Bob is destination, we want to send this message. Then we break that message in few parts, that is the, think of that is the packet, 64-bit blocks, and then we have in reality, if you do, before chaffing and winnowing, this is what happens, you do the break it in parts, and of course, in the parts there is no English sentence, it is all zeros and ones corresponding ASCII characters. You put message ID, you put message authentication code, remember SHA with HMAC, hash based message authentication code, you put message authentication code, and what we are doing, we are putting some garbage in it, chaff, we are putting some chaff in it, we are putting some message ID, some fake MAC and all that stuff we are putting in. And how would that help? Because if I do that, now when message would be sent, the green ones are actual message, the red ones are the fake ones. Remember that red sentence we had? So, when that happens and it goes to Bob, Bob is able to kind of figure out what it is, but the whoever is eavesdropper has no clue how to separate those chaff from the original one. So, the question is, can we, this is exactly what we want to do. We add some chaff, other people will not know, and when this idea came to us or thought about us, first thing occurred to us, nah, it is not going to happen. Can anybody tell me why this is not doable in the first thought, or what is the problem with it? Network has already problem, resource constraint, you are putting some more garbage on it, you are going to slow down the average network latency will go up, the execution time will go up. How is that a good idea? That is never a great idea, right. So, but the way we kind of implemented, that is another animation. So, the way we implemented is the following. So, then think of this message we divided in 3 parts, and everybody is trying to steal, and then what we did is one of the packet I do not want to send through that path. One of the packets I will use a different route that Eve has no access to, and all these 3 packets will get combined. Alice will exactly know what I sent. Eve will have a total wrong view of the message. Eve is seeing purple, but actual black was sent, Alice is getting the right message. The question is, how do I achieve this? The way we achieve this idea of encryption, if you get all the packet, you actually get the message, otherwise you do not. This is known as, I will introduce that, this is known as all or nothing transform. Again, these mathematics I am not going to introduce. This idea is, if you do not get all the packets, you are not going to know what the content is. Think of this as a weird encryption technique, all or none. Once you have this technology all or nothing transform, on top of it, so this picture this says if you get all of them, then you know it. On top of it, we are putting this chaffing and winnowing on only one block. Think about it, I take the whole message divided into lot of blocks, only one block actually I encrypt, and that too, that encryption is through chaffing and winnowing, only one block. Other blocks, I mean, it may seem silly, other block we keep as it is. So, just the analogy is actually wrong. Let us say I wanted to send a message, I love you, and then I and you can see, this word you cannot see. Now, that is not exactly what is happening. All or nothing transform has a security guarantees and fundamental stuff, and how, what is the idea of new, this the physical idea of new channel is nothing but one of the packet I am encrypting. So, that is the visual illustration of going through another path, is actually not going through another path, it is just that one of the packet I encrypted. So, in this picture it seems like Eve is not getting which one, the green one, but in our life green one is also going through it, but it is just that green one is encrypted, and because green one encrypted, Eve cannot figure it out. So, therefore, it cannot figure out the whole message right there. Any questions? That is basically the key idea, and how do we do that? Let us say this is your message. By the way, this message breaking up packet, this is for any network, not just network on chip, even the general purpose network. This is the idea, you take a message, divide into blocks, and those block we are taking one block. Now, you can take more block, that is fine. You take one block, and then we are trying to put the kind of each of the block, the wheat part is actually the main information part, important part, real part, and the chaff part is basically some garbage. So, this basically in the wheat part you may have say data bit, counter, message authentication code and all that stuff, actual message itself, and then the chaffing part is basically the garbage we are adding. That is basically what we are trying to do, but it builds on the guarantees of all or nothing transform. The details I am omitting, but it was not the example I took, I love you, and I and you part you can see it like a clean text, it is not that. So, actual, as I said, actual computation is really intense. On the sender side, we kind of do all or nothing transform, even computing all or nothing transform, that itself is resource intensive. So, we kind of took some ideas from quasi group, from mathematics, and tried to do that. Even the MAC computation, the message authentication code, that is also intensive. We kind of tried to do pre-computing this thing, and how do we add the chaff. Same thing on the other side is exactly opposite, pre-computed MAC tags, winnowing, removing the chaff, doing the inverse all or nothing transform, which is again in the we operate on the quasi group, and we basically get the message. And so, then we kind of run on real benchmark, and typically in on chip network domain there are two benchmarks that are widely used, the splash 2 and the parsec, and they also support parallel multiple benchmarks are running on the multiple core at the same time. And the kind of story then I wanted to show you is that if you do not do anything, if you do not have any encryption, you are just sending the data as it is, then execution time is the inverse of kind of performance. So, then basically you will have really faster execution time, right, it takes less time, less time to execute a program, that is a good thing. If you are putting for example AES with full encryption, we are giving advantage AES of parallel counter mode, then it is going to take that much of time. This winnowing and chaffing basically gives you a reconfigurable security option. So, what that basically means that you are able to choose how much security strength you want, whatever guarantees I did not talk about, and how much overhead you are willing to put. If you keep going the number of chaffing and winnowing bits, how many bits you want to add, if it goes too far, it might take actually more than if you just implement using AES. That is not a good, it performance penalty might be too much, but it has one more advantage. So, by the way, this is the packet latency or average how long each packet takes in the space, and this one is total execution time. So, technically speaking, we are using somewhere around 64 bits. So, technically performance improvement wise, this solution actually not great, unless one of you can come up with a better solution, but it has strategic but which you can control. If you want less security, then you can have that security and performance trade off, but what we are able to achieve here is basically basically what you are able to achieve here is the. So, as I said, the performance improvement is very tiny with 64 bit, but what we are able to achieve is the overhead. So, implementing AES and all that and implementing chaffing and winnowing, there is a significant improvement both in area and power. That is basically the idea. So, it is not free, it is still lot of hardware, lot of thing, and so if you are working in this domain, you want to do that. The performance and delay number you directly get from GEM5. When you run in GEM5 simulator, it dumps the data, you look at that data, you get the value. To get these numbers, you have to write your design in VHDL or Verilog, use for example Synopsys design compiler, compile it, synthesize it, and then the design compiler will give you those numbers, generate that area report, power report, and from that you get the number. So, you have to synthesize your AES 128 implementation that already exists in the community, then you can do this kind of stuff and so on and so forth. Any questions on encryption using chaffing and winnowing? Yes, please.
So, security comparison, how much secure is it as compared to that, maybe a brute force level?
Right. So, security comparison comes from the fact that chaffing and winnowing, all or nothing transform has some security guarantees, and that guarantee if it hold, then it would have comparable security to AES. But as you realize, when you implement and you do certain stuff, that kind of violates. So, AES is by itself. Here we have the vulnerabilities of the chaffing and winnowing and vulnerabilities of the all or nothing transform, both combined together, that may create some situation. But if we are building on top of all or nothing transform, if that guarantee is hold, so then it would be comparable to AES guarantee. Again, if you see the paper, it would have those guarantees discussed. So, the next thing I want to discuss about is called multicast authentication. Recall we are still discussing what kind of security enhancements we can do on the on chip network, design for security solution. So, what is multicast authentication? Let me define the context first, then I will define the threat model. When a source is, again this is the actual, if you think of this as the CPU, this is the network interface, and you can think of either it is there or this is basically the router. So, every node has those three components, right. So, when source wants to talk to destination, this time they want to talk to multiple destinations. Can you tell me a scenario when somebody want to talk to multiple people? What are the context? Broadcasting a message. In programming paradigm, when do you broadcast a message? If you took computer architecture course, where did you see somebody broadcasting to somebody?
Routing, sir, we want to update the table and everybody wants to know the state of the table.
Right. So, you are right. So, let me draw something. So, this is P1, it has a cache L1, P2 it has a local cache L2, and they probably connected to main memory. In this context, think of at some point processor 1 wants to let us think of a variable x with some location let us say value 5. Processor 1 let us say wants to read that location x. So, x equal to value 5 comes in here, let us say 5 seconds later P 2 wants to read it. So, x equal to 5 goes there, 3 seconds later P 1 wants to write to it and changes it to 10. Now, because we use write back policy for performance, now we have a problem. This is we call as cache coherence problem. Everybody has their local data. If 3 seconds later P 2 wants to read it again, it will say, oh, I have a heat here, it will read a value, but that is the wrong value, it should be reading 10. The way cache coherence protocol works, they maintain I am not going to get into the cache coherence architecture lecture today, but basically it maintains lot of table through Snoopy protocol or other protocols, directory based protocol, depending on whether it is a symmetric shared memory architecture or distributed architecture. But what will happen if somebody wants to write, it would inform on the bus, by the way I am writing to this address, everybody would be looking their location and they will invalidate it. The 5 will not become 0, but there is a block, invalidation block, like the way you have valid block, dirty block, there is a block that would mark as invalid. Now, this message of broadcasting that I am writing to 10 invalidate, in this example I talked about only 2 cores, it could be 32 cores. So, if somebody writing remaining 31 cores is getting that message, invalidation message. So, in this example I am informing 3 people, but cache invalidation depending on how many people have that data, it could be point to point, it could be broadcast, but multiple people are getting the same information. There are many such scenarios, but cache invalidation is one example I want to bring up to you, that if one party does something, lot of people need to be informed, same information. But for our discussion it is not important. Remember when you talked about garlic routing, it does not have to be exactly same message, right. It could be some of the path it is going through, maybe it is going here, maybe it is going there, but this path multiple people are going through. So, that is the idea of multicast authentication. So, what is the difference? Difference is if multicast story or communication did not exist, how would you do the authentication or encryption for it? Let us say nobody knew about multicast, but this level of communication existed. What is the traditional solution that exists if you want to encrypt them or add authentication to them? Treat them as individual, do not treat them as 3 messages coming from same person, ignore that information, just treat this color is going to this one as one color, treat this particular one as a different color and treat this one as a different color. So, 3 different messages, it just coincidentally so happened source is same, ignore that, just encrypt them independently or add authentication independently. So, then that would be our, when you work, research or publish, you have to say what is the baseline, whom am I comparing with. So, our comparison is with, if we did not have this notion of multicast, we have unicast, single source, single destination, and we just treat those messages same message, but we basically treat them independently, create 3 copies of it, encrypt it, put authentication and send it out, AS to D1, AS to D2, AS to D3. That would be the expensive one. Can we do better? That is really what we are trying to solve. And why we need to solve that problem? Because this here is the threat model, that although AS is sending information to D1, D2, D3, there might be a malicious node in the middle, this one, it might send invalidation messages pretending as S. If you send invalidation messages, what is the problem? Is that a problem? So, some data was in the cache, you are saying you need to invalidate because I am writing, but they are not writing, they simply want performance penalty. This is called performance degradation attack. Why? Because remember, if you send a invalidation message, that processor will mark that cache data as invalid. Next time it wants to read from the cache, that data does not exist. It has to go all the way to main memory, fetch the data, it is creating that cache miss, but in reality because this is a fake message, there is no invalidation. That data should have been valid, should have been in the cache, it should have took one cycle to read. So, this type of attack not only it breaks authentication, somebody pretending as somebody, it also can lead to. So, remember we talked about the payload, it could be functional change, this particular case it is a parametric change like performance, it creates a performance overhead, which eventually can lead to denial of service attack. If performance overhead it creates so much, nobody else can get the service, it slow down so much, then it is a denial of service attack. Any questions? So, this is basically our threat model. Now, so the way we are kind of implementing, so there was a kind of a very lightweight hashing technique called CFAS. We basically tried to take advantage of it and try to come up with an idea. So, this case we are trying to solve the authentication problem. We could have treated it as a 3 different message and added message authentication code, each of them independently. Now, we are trying to construct one message authentication code for all 3 of them, and so that is basically kind of we are doing not in a naive manner. Naive manner would be create 3 of them, put it in the same message. So, message part is not replicated, but 3 message authentication code are padded next to each other. When they change their path, let us say we are going together, oh this is already. So, let us say we are going in train together, then you are going to get down at your station and I have 3 gifts for 3 of you. When you are getting down in the station, I am going to give those gifts. So, if original thing created 3 MAC, the message authentication code 1, message authentication code 2, message authentication code 3, then when they separate out, here in addition to passing the message, I will give the message authentication code 1, because this is travelling together, and then here when it is separate, I will pass here message authentication code 2, here I will give message authentication code 3, because this is where all the 3 got split, but this is kind of high overhead, because each message authentication code somewhere in the vicinity of 128 bits. So, then that is too much of overhead. So, we came up kind of created. So, we still want to maintain that level of information, you still have to maintain something and provide something, and how do you kind of optimize that, that is what we are tried to do, and opposite side you have the exactly inverse of that. So, what I wanted to show is basically because of this what kind of average packet latency, which kind of reflects what is the execution time compared to if you have no authentication at all, no authentication, they are just going and nobody cares. So, then whatever overhead would average packet latency would be, ours is this is 0.4, 0.5, this is 0.1, 0.05, 0.1. So, our one is lot of overhead compared to that, but it is significant less overhead if you do separate authentication for each of the packets. If you do unicast authentication for each of them, it is significantly. So, this is like kind of 90% from here to here. This is still lot of overhead, because this is 0.05 to 0.1, but that one is significant number. So, that similar trend kind of reflected in the total kind of execution time also. Any question on multicast authentication? So, what is the key idea? That a source will send the same message to multiple people. Do you want to have a separate authentication code for each of them, or can you do better than that? No questions? Okay, now I am going to talk about the last but one component. So, the first one is reconfigurable security. We have introduced so many ideas here, right. So, then on a network on chip, do you want to keep all of those security components or do you want to reconfigure them, and why do you want to do, what is the context? You look at any system on chip device, it this is basically comes from the ARM little big design. So, ARM is the first company to show. Before ARM came in, everybody has an idea, if things are homogeneous, everything is equal, the performance would be nice, because then compiler can generate nicely, everything is equal. First ARM came in and showed, if you have one processor that is less powerful, less power hungry, another processor really power hungry, very fast, that kind of gives a nice overall kind of productivity. But anyway, so this is from that little core cluster, and pictorially shown as small, and big core cluster and so on and so forth. And if we kind of plot, no matter what program you run, this particular case you have a display, memory, accelerator, and how they talk to each other. Depending on which program you are running, even within the same program, depending on what time you are looking at, the how many programs are active and how much time it is taking, how much resource utilization, memory utilization, these things goes up and down, it is not constant. It is not constant, and this would be easier to understand if you think about a program that is computing, let us say 2 for loop, even the same program, the amount of data you are loading may be too many array references, too many array references, this one maybe have no array reference or maybe just one. So, then the number of cache misses, cache hits that happens in this for loop is going to be significantly high compared to this for loop. So, if you look at a plot and look at kind of plot just kind of misses, you will have lot of misses followed by very little misses. So, there is all these kind of variations depending on the architecture, what is happening in a given specific time, there would be huge variations. And if there is so much of variation, same story holds even vulnerabilities. Amount of vulnerability that is out there when program is running, it changes. If you are using your phone in a coffee shop, that Wi-Fi versus if you are using Wi-Fi at your home, the level of vulnerability is different. Or maybe the amount of battery you have in your phone, maybe then you want to disable your security. So, if you do not have that feature, then it is not a great idea. So, reconfigurable security is good for anything. So, in this context we are talking about on chip requirements, because dynamic behavior, usage and all that changes. So, what we are trying to build here, or what we build that architecture is basically a multi-tier kind of architecture. Some of the features we want to keep always on, or maybe we turn on, and if you have more battery, if we think you do not feel safe, then you put one more tier on and then you make one more tier on. And what would be included the tier, we had a sample example, tier 1 should have bare minimum encryption, if every packet should be encrypted, encryption feature should be on, authentication if you want more, and then some runtime detection, that would be if you still have more, or if you are still little worried, you are in a different country and whatever, then you might want to do that. There is even a easier solution than this, anybody knows, when it comes to phone, you keep it off. People who are living comfortably the days there were no phones, what is the big deal, right? You can solve the problem at the root itself. Anyway, if we are not planning to solve that, what are the security primitive, what are the reconfigured parameters, this is just generally a general idea, and this is basically what we looked at, and we will probably have. But when you propose certain things, you have to propose it all the way. How in the system on chip fabric, how would it work? So, you need some kind of engine like the configurable security engine, different components would be there, whether that is a processor and analog to digital converter, controller, whatever it is, and there has to be some form of communication. That reconfigurable security engine is kind of maintaining the security policy. It has a lot of overhead, although it may not be obvious. The assumption is security engine kind of has directly or indirectly access to everybody. that is one. Second is if security engine thinks display controller is doing funny stuff, so then it should have the ability to put some more restrictions or checks on the security controller sorry display controller or whoever is talking to display controller. So, it is kind of not a very distributed parallel kind of story, it is kind of little bit of centralized and single point of failure problem. But anytime you use a security policy enforcement engine, you have to either you decide I do not want to do this, or if you want to do this you have to take this overhead and this kind of trade off, unless one of you can come up with a better architecture. So, at the end of the day in layman terms what it is, if this is your network, think about it, this is your IP, let us say this is CPU, this is your memory, it will have its network interface and then the router. In the router you have all these things that you can enable and disable, encryption, authentication, what is SAG? It does not matter, and then RRG, never mind. So, all these kind of features, this is definitely denial of service attack. You will have all these features that you can turn on, that you can turn off. When packets are flying through the router, you can enable those security checks or you can disable the security checks. That is kind of how you implement. Any questions on reconfigurable security? The final one I am going to talk about, going back to, remember we talked about security assertions and we talked about in general what security assertions are, and now I am going to apply this for verifying network on chip trust. So, basically you have all these techniques. First of all, if you do not have these techniques you can still apply, and we are going to use it in two ways. If you recall our discussion on security assertion, this can be used two ways. Assertions are properties. So, you have to deal with two things, what are the properties you want to check, right, and how do you derive those, that, and once you have that, how do you want to use it, these properties. So, these properties you can use formal verification. If you have a model of the network on chip, you can formally verify those properties, or which would be similar to any design for that matter. Only difference is all these properties will have source, destination, communication and all that properties. If so, for example, by knowing the network on chip, if there is a request, next cycle there should be an acknowledgement. This x means next cycle. If you think it may take 2 cycle, you put 2x. So, it has to be specific to that network, request, acknowledgement, or if you want to check for authentication, correct implementation, nobody should be able to figure out better catch. So, you can spell that out and complicated properties. You can do formal verification that you can guarantee that design has no flaws for that property, or if you are not able to verify, then you put in the design itself, let us say VHDL Verilog code, C code, you put that as a assert statement, and all that complex equation you put that in the assert statement. During runtime it would check did the assertion violate, or you do both, that is the thing. Now, so how would then it work? So, basically the way it would work is that you need to have some kind of threat model. What are the threats we are looking for? Authentication, then the eavesdropping attack, then all of that stuff, anonymity attack. We will talk about a lot more attack in the afternoon. You already know what type of attacks are possible, and you are generating those kind of assertions. And when you generate those assertions, this is your network on chip design, it could be VHDL Verilog model, and when assertions are generated, you put those assertions there, and then you can kind of this is kind of the pre-silicon before fabrication. After fabrication, you can this assertion, if you want to map it to post silicon, those would be the trigger or the checker, hardware checker. And so, you will have design and tracing and hardware checker, and it would work. Now, let me give little bit of perspective on the post silicon, because this may not be clear. Let us say your assert statement is assert A, it does not matter what A is. In general, this expression is a lot more complicated. If it is a signal A you want to assert on, the assert function is a piece of hardware. How would assert work if it does not have access to that variable? right. In your program you can say, well, I am putting this assert if file pointer and all that stuff you are putting wherever you are opening the file, that is not hardware designed, right. You cannot, whenever you are computing a signal variable A, you cannot put a hardware there right there saying okay, now if it is failing just do it. So, you are putting that hardware somewhere else. So, you have to route that signal, or there is another choice, or there are trace signals or trace buffer. Remember, in the silicon you have billions of signal and there is a buffer which stores some of them for little bit of cycle, there is a tiny buffer 1024 cycles and maybe 128 signals. Those signal when you select, earlier our selection was for debuggability, you want to select the signals that helps you debug if anything goes wrong when it goes to the customer side. Now, your objective is if you have any assertions, you want to maximize the visibility of those signals. You may not be able to trace A, but you want to trace somebody who can tell what is the value of A, you can derive value of A. So, then the lot of other subsequent functions will change if you want, when you consider the assertion and network on chip, and that is basically kind of, I believe that is all I want to talk about in verification. I did not want to show the properties and assertion, we already talked a whole day on this one. Any questions on verification of network on chip? That brings me to the end, we will meet after lunch at 2:30 p.m. Thank you. Good afternoon. In the morning we talked about different types of network on chip attacks, and in the context we basically covered how we can build design for security metrics. So, now we are going to basically look at how do we detect some of these attacks during run time. Whatever we talked earlier is design time, what we can install in the design itself. Now, we are talking about how do we detect them on run time, and basically we are talking about attacks and countermeasure focusing on machine learning techniques. So, we will start with denial of service attack. This is a well known attack in the computing community. This is also well known attack in network on chip community. What is the basic idea? Basic idea, if among these components in the design and in computer networks, different computers all across the globe, if they want to do denial of service, then they basically they have to overwhelm someone. In this example, by realizing the fact that all these components, processor, DSP, GPU, everybody will go and try to access from the memory, and if memory is the bottleneck, let us overwhelm the memory with lot of fake load requests. If somehow this attacker can send a lot of requests to the memory, anybody else trying to access the memory, they will face slowdown, and in the worst case they may not get any response. So, that is the denial of service, and the name basically says it all, that it denies the service. Now, in this particular example we are talking about denial of service for memory access, but in general this idea of denial of service applies to anything. So, for example, if you are doing a hotel booking, hotel reservation booking, and that web page is down, not because the computer is not working, because somebody sending lot of fake requests, millions of requests, so that that server cannot handle those many requests in a legitimate time. And that is why denial of service goes back to what is its intended service. In this example, memory's intended service is load and store. So, if somebody sends a load request, if you are not able to fulfill it in a reasonable time, or you are not able to fulfill at all, that is the denial of service, right. Now, there are many variations of this denial of service. So, for example, performance reduction, that is not really a denial of service, but it is basically quality of service, degradation of service, or that we call as quality of service. When you buy any service, whether it is your internet, phone, whatever it is, you have some expectation, or data plan, unlimited data plan, then you are not able to use the data, then that is a quality of service. So, that is why denial of service, and also then there is the degradation of service. And most companies do a graceful degradation of service. They will not completely deny it. If you go to a different country, maybe the data or that rate will not be so high, it may not be fast, but at least you will be able to do certain things like your messaging and so on and so forth. Any question on denial of service, how it is created? It is basically this color, this is in thermal graph, this color basically says wherever you see a lot of red, there are too many messages there, compared to where you kind of see kind of green color, so which is right here, or you see yellow color, compared to that orange is higher, and red would be extremely high amount of requests going through. Now, there are different attack scenarios. So, when denial of service attack happens, our normal assumption is there is only one attacker. This is a simple 3 cross 3 grid. So, whoever is attacking, that is attacker, and whoever is the denial of service, that is the victim. But in real life, this one is not the victim. The people who are looking for the service. So, for example, this some sender wants to send or want to do a load request, this is actually also a victim. When ransomware attack happens to a school district or a hospital, sure, hospital is the victim in by the definition, but the people who could have got the service, life saving service, they are denied of their service. So, that is also a denial of service for them. So, any attack on anybody, any community is actually an attack on the society, it is an attack on the nation. So, it is actually much more powerful than that. Now, in many of the time attack is not by alone, there is no lone wolf attack, it is basically collective. For example, here A1 and A2 are the malicious node and they are kind of sending fake messages to the victim node. It can happen that way, there might be little overlap. Some of the time the overlap could be kind of total overlap, and some of the time the way requests are, this might create a loop. So, depending on how requests are, who is requesting whom and who is sending fake messages, how much fake messages, the detection and localization problems are different. Any questions? So, aren't there any kind of problems or solutions that are in the community? So, there are, and one of the interesting work is that if you have a malicious node, let it be there, but make sure it cannot trigger. Once it triggers, it will send lot of fake messages, right, and there are many such stuff. So, how do we kind of address this problem or the known solutions in the computer networks community into some kind of resource constrained community? How do you implement very simple thing, and using those simple things you can detect at runtime that an attack is going on right now? How do you do that? So, the key idea is, if you observe, so key idea is, if this is source, if this is destination, it does not matter how they are connected, then if there are two people, you kind of look at how frequently they talk. If they are talking too frequently, that is how neighbors get suspicious, something is funny in this house. If your behavior is suspicious, people tend to figure out something is not right with you today, something is not right about you, because you normally, when you meet me, you normally smile, and today you are not smiling. Normally you play in the afternoon, I have not seen you in the afternoon for quite a while. So, that is the pattern. So, that is why if there is a in this particular example we have a communication pattern, and deviation from that pattern is treated as potentially denial of service attack, and then you can further corroborate with that. Now, recall, if you are playing few days and you are not playing, that does not necessarily mean you are dead. You might have health issues, something might have happened in the family. So, in this particular example a pattern changes little bit, that may mean the input changed. Sure, same programs are running, same behavior, but maybe the program, the input, earlier it was sorting 10 elements, now it might be sorting hundreds of elements, all that stuff. So, there are variations, environmental variations, normal variations, and that variations might cause a change in the pattern from pattern to pattern prime, and you do not want to detect as a denial of service attack. So, that is the difficulty, and later you will see machine learning takes care of it. Right now I am going to talk about how you do without machine learning. This was early work almost 6-7 years ago, then subsequent machine learning work basically addressed this problem of uncertainty. Now, how do you do any of these curve or any of these pattern you look at? Let me see if the animation works. So, you have bunch of routers, right, and remember each router is connected to each of the component, could be CPU, could be memory, and then if you want to send a message, messages are going through, and as you see when messages are going through, we are looking at the what is happening in this router. If this is time scale, and only thing this is the time scale, only thing we are measuring at this time scale when the requests are coming or emails are coming, we are doing basically that, and that is how we create for every router. If the behavior of that router is different, then there is something funny. Now, in this story you have to assume somebody is trustworthy. If router itself is malicious, why would it self identify or report any of these things, right? You have to assume maybe router is trustworthy, the network interface is not, or network interface is trustworthy, somebody else is not. That is the key idea. So, once you have this kind of pattern, then you, so this particular example we are looking at, different router in different times. So, blue could be regular stream and red could be the compromised stream. Now, as you will see later in machine learning is going to figure all of this out by itself. Once you train it with saying this is where denial of service attack is happening and this is where normal access is happening. Now, there is a silver lining here. When denial of service attack happens, you have to send a lot of messages in a short duration of time. So, if you are thinking, well, a violation of 1 or 2 packets, would it be treated? No. 1, 2, 5, 10% it will not, because that would not be enough to create a denial of service attack. If you are sending earlier 10 packets per second, now really you have to send millions of packets per second to suddenly overwhelm some memory controller, for example. Any questions? So, basically then different events and packet arrival you are looking at, and so absolute numbers might not mean much, which time what, and maintaining that is also a problem. So, what we want to do during some time scale, we want to count how many events happen, how many email came in, how many packets passed through me in different time scale. That is why you see a sudden jump. It is not that something happening, it is just in a time scale you count and you kind of plot it, and as you can see it is kind of incremental, right. So, let us say I do not know, this number is 4 packets you have seen, and then here no, this is less than 4, let us say this is 4 packets you have seen here, and then few minutes later you are seeing 8 packets. That means, this is 4 plus 4, that is why it is a stepwise function. You kind of have a curve. So, we call it some form of curve, and then if you see a curve that is different from that curve, like this red one. Now, how much different would be treated as a denial of service, that is different, but if you basic idea remains the same, this is your expected curve, if this is the curve you are seeing, then you kind of have a, there is something funny here, whether that is enough for denial of service, that is different. So, there are a lot of mathematical notions we have developed, but this is the key idea. Once you kind of have a bound, preferably some kind of upper bound, and anytime you see a pattern. So, this is my bound established by analysis, this is the bound I have, the basically the green area is my bound, and then the blue line that you are seeing, this is at particular time when you are monitoring, you are simply saying what is happening with that pattern, and then blue line, as you can see, it is in the green shaded area. So, it is perfectly fine, it is normal. But if you see something that is of that outside your predetermined bound over a period of time, so then that is suspicious, that is potentially denial of service attack. Any questions? So, this is about so packet arrival curve, and also so this is the source, and then is the destination, also same thing needs to happen. So, there are 2 curves. So, if somebody, the router is trying to measure here, it is kind of plotting what is happening in different time step, it is marking on its side what am I observing at my point, and it keep on plotting that, and it is getting some of those information captured. So, during using these kind of information, I would be able to plot what is a normal operation at different time frame, how many packets, what is their average latency, and all that information. That is normal operation, and attack scenario something of this nature at time step the hop count 4. Somebody from 4 hops away from me is sending too much of data. You see in 4, what was the expected one, 4 hops away. Now, it does not uniquely say who is 4 hops away. If you do a mesh and if you have a number, let us create 3 by 3. So, if you are plotting something about this dude and it is saying 2 hop away, lot of people are 2 hop away. So, this one is still this one, if it is not XY routing, this one. So, this is one candidate, this is one candidate, this is one candidate, it has 3 possible candidates. You still have to kind of reduce from these 3 who is potentially the one who is doing this one. Any questions on this about counting, having a bound, maintaining minimal information and then trying to detect. So, the overview would be, as I said, you build a kind of curve or communication model where certain kind of pattern is expected and that is the bound, and then when in real time. So, this one you do during design time, think of machine learning will do the similar stuff, and real time you do the detection by looking at somebody who is deviating from this bound. So, that particular red line compromise stream, and now this analysis further you feed it to the rely on the destination router to see what kind of stuff happening, then you can kind of identify and localize. Initially you may have multiple candidates, and I will show you how do you kind of then reduce to which specific one actually responsible for this attack. Now, what you do with it, there are a lot of research in the community. So, something similar to that, once you identify the node, the nearby nodes will never forward any data from that node. You kind of what is it called in the virus and antivirus community, when certain files you think is quarantine. So, then it thank you. So, then you will quarantine this particular node by not forwarding or allowing any message from that node, but assumption is then is only one malicious node. If there are too many malicious nodes in a society, there is not much you can do. So, we kind of talked about this all of this mathematically we talked about it. I am going to skip up that, and for this attack detection there are many variations of this algorithm that are much cheaper, much cost effective. One of them is known as leaky bucket algorithm. So, basically all these bounds can be approximated by minimum set of periodic staircase function, and then packet stream, packet arrival, how do you take care of it, and there are a lot of interesting ways of solving this problem. Now, localization, as I said, is kind of tricky, because as we said first you get an idea that the person who is doing this is 4 hop away, and you have to understand for this to happen the person who is under attack is still not dead. If that person is dead, that server is not working, this information cannot be communicated to anybody, right. So, then we are trying to basically figure out who is kind of, let me see if I have examples else. Yeah. So, once you kind of figure out 4 hop away, and in this particular example we are kind of so this is the victim in all of these examples, this is the victim node V, and this is the attacking node we are trying to figure out, and this is somebody S which people start suspecting. But so basically how do you differentiate an attacker from somebody who is suspicious, because if you are just looking at congestion in the route, you would be thinking maybe the congestion is getting from S or A. You have to somehow kind of eliminate that story, and through different mechanism how do you figure out. So, for example, here, so here also it is kind of initially difficult, here it is also kind of hard to for these people it is hard to say where it is coming from, it can come from any of them. So, similarly there is some there are, let me see, I have an example for that. So, let me skip all of that. So, whenever we have multiple suspicious one, the victim is going to send a message all the way to the potential attacker, and then it basically a counting game. So, for example, when the first one A launches an attack on V, then S and D are also communicating with each other, everybody else is D and V both detect an attack. In this example both D and V says we are under attack, D discovers from DLC that S is a candidate MIP. So, because D is under attack based on distance and whatever, it is kind of figuring out, thinking that S might be the one who is causing the problem, S might be the one who is causing the problem, and now we have to do the eliminate S and identify T. So, V discovers DLC at A is candidate MIP. So, multiple people might be calling multiple people as potential one based on their observation, and because they are in the same path, that is why it is a problem. And then if you do the, so first is S receives a message from D saying you are probably the not a good person, and then S receives another message from V through the same port saying A is a candidate BIP. So, V is saying A, so then basically this becomes 2, and in contrast V is saying A is the one, so that becomes 1. So, this process once you compute, then basically you can eliminate S based on the algorithm, then you can eliminate S and then that would left with A. It does not have to reply saying oh I am the bad one, A will never do that. It may receive the message, and whoever is receiving the message you have to understand it is going through them. If it was direct message, that is a different story, but it has to go through them, that is why all these countering can kind of work. And then so that is how you can detect and eliminate. So, in terms of experiment, something I did not get chance to mention. So, GEM5 is the architecture model. If you want to implement on research on network on chip, so there are many variations. Garnet 2.0 is the library you connect. The GEM5, the standard one itself, does not understand any network, it only understands architecture. You have processor, you have memory, you have cache, all that you can configure whatever it is, but multiple processor talking through a different kind of communication fabric like mesh, point to point, bus. If you want those facilities, then you have to go for Garnet. But if you simply want to have a single core, multi core architecture, cache coherence and all that stuff, just pure GEM5 would be fine. And but as I said, when you want to do ring, mesh or any kind of different types of configuration you want to do, then you use that library along with GEM5, it will do that work for you, or you want to choose. So, what you are showing here is that how much time does it take for different kind of experiments, different kind of scenarios, how much time does it take to attack. I may have a better result, yes, right there. So, if we have one, so y axis says how much time it takes, x axis says how many people are simultaneously trying to make the DOS attack. Here 4 people or 4 nodes, 3 nodes, 2 nodes and 1 node. Do you see anything interesting? And these colors are for different benchmarks. Do you see anything interesting here in terms of detection time, DOS attack detection time for different benchmarks involving different scenarios, each of them is independent. So, these dots are independent, that is one kind of scenario, this is a different scenario, this is a different scenario and this is a different scenario. Each of the color line is also different because that is for a different benchmark. So, there is a similarity in the story. What is the similarity in the story? All the benchmarks follow the same trend, and the trend that if one attacker is there, then it takes longer time, if multiple attacker is there it takes less time. Why that is true? Because if one attacker is attacking, think of any grid or any structure, right. If you are trying to figure out is there a chaos in the society, it might be difficult for you if one person is making a chaos somewhere next to the lake. But if 10 people shouting, 20 people shouting and all that stuff happening, or one road is congested versus lot of roads are congested, that would very quickly you will be able to figure out. That is the whole idea. The bound, whatever you set it up, crossing that becomes much faster, much easier when there are multiple people. So, that is why this number is really small. Remember, this is attack detection, not attack localization. You will see an opposite story for this one. So, real chaos, more people, right. Now, the opposite story that I wanted to show you is that when you talk about the localization, then basically attack and attack detection and localization time, then for different kind of benchmarks you are kind of seeing how all these kind of plays out. So, for different kind of benchmarks, the colors are different benchmarks FFT and so on and so forth, but relative to each other, the typically the localization time is small, but the detection time is kind of large relative to each other. But when you kind of go from 1 to 4, your localization time kind of increases. And if you kind of try to zoom in further for different kind of stories and scenarios, so the timeout period, victim to attacker packet travel time, when you are kind of have point to point communication. So, point to point is this square, which is, so these ones, these are different test cases. You will observe the point to point, the time is less, because when the victim is sending a message to the attacker, I think you are the attacker, point to point is 1/2 communication. But if you are thinking of a, let us say 8 cross 8 grid, which is the green line, you will see that that one is much bigger everywhere, and that is expected from victim to attacker. And remember, those counters getting up and down, that kind of takes time. So, that is why they are going to take little longer time. So, any question on denial of service attack detection? I wanted to introduce another concept here. So, architecture community, when they do research on network on chip, and early years like 10-15 years ago, people used to say, well, it is all academic exercise, who cares, because nobody in the community building it. So, Intel is one of the first company to build this night landing architecture, and that essentially implements this kind of mesh network that we have seen and talking about. So, this is the exact, and you can configure, unless GEM 5 comes with some feature to configure it, you can configure for night landing architecture. If you are working in this area and if you are not able to do on real hardware the results or research, the closest you can go, you can modify GEM 5 with Garnet to model Intel's night landing architecture, which basically, this is not exactly the beautiful thing I have shown you, but this is, at least you can see there are different types of component, like some MCD RAM, memory controller, PCI. You remember, this is the bus controller, PCI Express and all that. So, I wanted to show an exact scenario. So, one is L2, where is one? One is here. So, one is L2 cache miss. So, that happened in this particular node. If you want to give it a name, give it a name A. So, in node A, there is a L2 cache miss. So, memory request sent to the tag memory. So, the tag memory request was gone and saying L2 cache miss, go and fetch the data from main memory. And then you see 2, from wherever the request gone into the tag memory or the directory who maintains it, it sends a request to the main memory, and this dark color is MCD RAM. So, which is basically the main memory. Request went to the main memory, then main memory basically forward to memory after miss MCD RAM, then it basically sends the request to this one. So, this is basically memory controller, and then memory controller gets the request, that is basically 3, and then finally, when this memory controller gets the data, what is this one? This is double data rate, some memory. So, this is actually the main memory, and then this data gets returned back to the A, that is the 4th item. So, this is essentially as real world as it gets, how the things are placed, and as you can see, these memories and all that stuff, memory controller, all that stuff are placed on the boundary node. Although the NOC research academicians do, they kind of tend to place them wherever they feel like, as if this is 1, 2, 3, 4, 8 cross 8, 64 nodes can be placed. Academic researcher put whatever they want to put wherever they want to put. But in reality, if you once you try to do fabricate and put things on the plane, and you want to have memory, lot of those SCSI cable and whatever it is easier to do it from the boundary of a grid than from somewhere from inside. So, that is why it is not a surprise that all the memory kind of stuff, memory, PCI, bus, all that are in the boundary. The middle ones are mostly the processing nodes like CPU, GPU and all that. Any question on Intel's night landing architecture? Yes, please.
So just regular TCP/IP protocol is being used and routing is on OSPF, sir?
I am just still thinking, is it network layer? It is network layer, you are right. So, it is not physical layer, it is not data link layer, it is network layer. Yes. So, what about it?
So, is the regular TCP/IP protocol being used along with for routing OSPF being used?
TCP/IP I am not sure, but the TDMA and all those protocols are all used. TCP/IP,
I am correcting TDMA and regular XY routing are used.
TDMA and XY
Many
routing.
things of a regular network are removed, and here you can get the real processor also.
And so
Even
what-
Intel P processor, so you can get from the market also, and you can put on your PC.
And so routing is being done by regular OSPF, sir?
No, not proper OS. Not
No.
not proper all layers. Only towards bottom 3 layers are there.
Right, sir.
Only bottom 3 layers are implemented, so not all the layers. And this processor in market it is available, so you can get from the market, and you can in your workstation also you can put this processor. And in your PC it will show around 288 core machines. That's actually very interesting thing. Intel P processor, it is available in market.
Thank you, Professor Sahu. So, now that we talked about denial of service attack and looked at a little bit of how real world network on chip looks like, on chip communication loop. Now, we are going to talk about how to do attack detection using machine learning. Let us do the attack detection on machine learning for the denial of service attack, which we did without machine learning. And the real motivation is all these attacks, including the one I just showed, statistical learning, that was 2019 work, and many other of those. The reason, the problem with them, all of them, is that it work on specific scenarios. If you know the benchmarks, if you know the context, you know the device where it is installed, then you can put a bound on it, and it is actually not an unreasonable assumption. Because remember, many embedded systems, or specifically real time embedded systems, relies on that bound, because otherwise in any real time embedded systems, including airplane and car and all that, how do you give a guarantee that if it starts raining, let me see if I can do raindrop, draw raindrops. If it starts raining, the front wiper of the car will start doing automatic wiping within 20 millisecond. How would you guarantee? Because it involves lot of software running, lot of micro mechanical devices getting activated, including communication. You want to guarantee all of that finishing within certain time. The only reason you can guarantee that, because the exterior environmental condition you can put a bound, wind, speed, sensing, all that stuff, cold, you can put a bound. So, therefore, many embedded devices, it is actually okay to assume that you know the constraints, and there would be input variations, but those variations are also well understood. So, therefore, it is not actually flawed, but it is just that if there are variations, then if somebody is taking 10-20% off the bound, then it is hard to tell. That is where machine learning kind of comes into the picture. So, this is the same story. So, I am going to skip that. So, the way then machine learning works here, or at least for the publications wherever the way authors have done, is basically the same thing that you understood in most of the things exactly same. Only difference is you gather the network on chip traffic data during training time. So, this is your training time, this is your run time. Top rectangle is training time, bottom rectangle is run time. So, during training time you basically want to run your applications and dump the data from the network on chip traffic, right. And then once you have that data, you train the machine learning model, as simple as that. Now, of course, there is the question of what type of machine learning model is ideal and so on and so forth. I will not get into the detail, and then during run time you still have to have a mechanism to real time data gathering of network on chip data, and then you send that data to some security engine, some kind of thing, and then you classify if there is an attack. Any question on this simple flow? You gather the data and train the model, now your model is trained, put that model on the real device, like a hardware in GPU or wherever you put that hardware, machine learning hardware, train model with those weight. Training is nothing but if you are for example taking a neural network, you basically decided the weights and how many layer and all that stuff, whether you have soft max layer at the end, whether you have multi-layer perceptron, whether LSTM, whatever you decided that type, you decided the weights of the all the edges. So, if you are thinking what weights I am talking about, let us say you used a machine learning model with something like this, then basically deciding these weights on these lines, these weights and this is layer 1, this is layer 2, this is layer 3, how many layer, how many node, what are the weights, that is basically the machine learning structure. Those weights, layers, all those gets decided during training time. That is the physically how it looks, and conceptually it essentially builds kind of a line between two kind of decision for classification. So, the details I am not going to go through, but basically it has a lot of steps and most of these steps are. So, once you dump all the network on chip data, then you have to somehow extract and analyze and categorize feature, and if it is a supervised machine learning, you have to label them, and then you do kind of, if there are a lot of redundant feature, you remove them, and in this particular one my students did Bayesian optimization. You can do whatever you want to do, then you do model validation. Remember this in addition to the training and testing, even some people kind of keep some more data for called validation. There is a minor difference, but it is not, detail is not important. Then feature importance, feature ranking, and so on and so forth. Now, you kind of figure out how is your model doing. And again in terms of feature identification and generation, what type of feature you can take, there are a lot of choices. So, basically where the data am I collecting from, the position of those data collection, what type of data is it, and what path does it cover. So, for example, position, are we taking data from the router, from the VNet, from the input port, from the output port, where are the data getting dumped or traced. And in terms of packet itself, fleet ID, remember when you have a message, what do? We take the message, we divide into multiple parts. In our term normal world we call them packets, right, but the way network on chip looks at it, everyone kind of divided into lot of fleets, and then we have fleet type and so on so forth, and a collection of fleets is essentially packet. At network layer we just talk about packet, we do not go down any further, but that kind of stuff, and then destination, source, and all that stuff, that is also kind of feature. There are a lot of types of feature, and which feature, what it is, that is also important. And you can put lot of new features that may not be even relevant for the packet. So, for example, in terms of hop, how many hop it took, current hop percentage, NQ time, and anything specific to your implementation, you can also take those as a feature. They may not make sense, but that might be helpful for the machine learning. And so, once you look at it, so this is what I wanted to show you, that in a real network on chip, this is viewing this way is better. So, this particular node is actually the CPU, or this is actually the memory, and this particular one is the network interface, and this particular one is the router. So, then whole NOC, this grid actually see, that is actually the routing network, the components are hanging from there. So, that router at some point will forward the data to its own CPU, data might be coming here or it might be forwarding here. For this router there are only two choices in a XY kind of routing. In a any other form of routing, it may forward in different directions. Sorry, let me see. So, then this is again Garnet, and as I said GEM5 and XY. XY routing basically means go in the x direction as much as you can go, then go in the y direction. So, there are many tests in machine learning, many scenarios you have to create. This may look really convoluted. All it means, this is a normal operation node 0 and node 15. So, in a 4 cross 4 in a 4 cross 4 story, right. So, this is 4 cross 4, this numbering is kind of the way it numbered. So, 4 cross 0 and 15. So, something, so for the one I highlighted, program is running here and program is running here, that is all it means. So, n 0 15 is just naming convention, it has nothing to do with machine learning. So, when you say I tested different scenarios, how do you name those testing scenarios, that is what we kind of encoded here, n 0 15, or if you see n 0 15 a 1, that basically means normal or good programs are running in node 0 and node 15 and attack program is running here. So, the attacker is here. So, you can create different scenarios and the total number of possibilities is huge. This is 4 cross 4, but researchers do 8 cross 8 and 16 cross 16. The number of possible paths, number of programs you can run at a time, number of places you can place the attacker and the amount of data it produces in the range of gigabytes to terabytes. And then how do you process them, read them, feed them to the machine learning, that is another nightmare. So, in the NOC research using machine learning, if you are trying to do that, you want to keep that in mind. You cannot just do some few scenarios, then what will happen if you are going to do very few scenarios, unless you are lucky or choose them really correctly, the kind of scenarios you have not shown to them your machine learning tool, then basically it is going to do wrong decisions. So, these are so this is basically kind of talking about what kind of machine learning algorithm do we explore, like XGBoost, it is come also with the Python library, random forest we already talked about earlier, decision tree we talked about. Even if we do neural network, what type of neural network, how many layer, and do we do Adams optimization, do we do the gradient descent and all that stuff and different other kind of sigmoid function at the end, how do you, which one do we kind of choose and which one will work, all of those exploration you need to do. And then when you are doing exploration, what you really want to do, your training accuracy or validation. If you just look at the training accuracy, because training time you are trying to choose, because eventually you have to choose one of them, and then if you choose, these are different. So, 2NN basically think of 2 layer neural network, 3 layer, and this is decision tree, this is random forest, this is XGBoost, LGB is one of them, light GBM. Okay, so and so forth, and then you kind of look at it and it is kind of obvious that this particular point is XGBoost appears to be doing the best. So, that is basically, so that basically means that if this the training story is expected to hold during real world scenario, then I want to go with XGBoost and then I pick that, or maybe then if I want to do detailed evaluation, then maybe I will just stick with maybe these 3 as a starting point, decision tree, random forest and XGBoost for network on chip scenario, and it is not a coincidence, most researchers basically use these kind of 3 of them. And this is what I kind of talk about, that when you have a data set you generated a lot of data set, you use kind of 80% of them, 70, 80 based on your choice, you keep them for training and 20% you keep it for yourself, do not show those. And what are these scenarios? Recall I kind of showed you these A, B, C. So, these are your scenarios, these are the kind of different scenarios for which you are kind of doing the training. For example, if I am doing this training, this is normal and attack scenarios, and these are the test scenarios, that the data for these, when you set it up and then generate the data, those data you did not show it to the machine learning model during training. So, that is why it is kind of a valid testing scenario. So, again, so hyperparameter tuning is a classical problem in machine learning kind of training. How do you tune and what do you do, what kind of optimization you do, learning rate, estimation, depth and gamma functions and all that is important, everybody knows about it. and model validation also I talked about. And in terms of feature importance, in this particular research the explainable AI was not used. If explainable AI was used, this kind of evaluation, which router believes which feature is more important, as you can see it kind of varies. So, different type of router if you look at, they have their own ranking. So, it turns out, let me see, it turns out everybody thinks traversal ID is the ranked one, everybody thinks that way. Oh, it turns out max packet count is number 2 by everybody, but other cases there are some variations. I do not know where 3 are, 3, 4 kind of mingled here. So, if everybody thinks somebody has the same, then if you have to take 2 or 3, then probably this one, and where is the 2? 2 pack here and 3 here. Packet count index, these 3 would be kind of, but if you use explainable machine learning like Shapley value analysis, it will give you the ranking. And attack detection accuracy, again you use the different kind of scenarios, and then you kind of look at the result for different kind of scenarios. Again remember, these are the new scenarios which was not exposed during training time. What you are trying to figure out, what is kind of your accuracy number, and so what kind of accuracy number, 90, 98, 99 and so on and so forth. So, this is basically the accuracy of this machine learning algorithm. And of course, when you do kind of machine learning, you have to consider what are the overhead when you are doing this kind of stuff, because machine learning is trained offline. So, then the training time we normally do not consider as a thing, but packet header is the default one, the power and area overhead of having so 2 NOC. So, this is another idea floated by the community, which is, and in fact the companies also kind of consider that, do you want to have one physical network on chip, one network on which everybody travels, or do you want to have 2 network, physically 2 parallel network. Now, you can time multiplex it. So, then one can count as 2, and then there is always kind of voting towards having 2 different network and willing to pay very small. So, 2 network is actually not double, I want you to understand, or area overhead is 5 to 10%, but it gives you kind of double the bandwidth and much better performance. One is for functionality only, even if you are not doing security. Think about these are all these cache invalidation messages, that is nothing but saying go and mark something, write something 0, and normal load store and cache invalidation messages. In fact, when you do in computer architecture, when you do, if you have played with semaphore like PS and VS, you lock and you unlock. If you played with semaphore, you know the semaphores are kind of implemented with load linked and store conditional. It tries to load a location of a value and try to see is it 1, then I got the lock, I make it 0. But when you are going to try to make it 0, many other processes are also going there to try to make it 0. So, that would create too much of traffic, and those load store instruction are not the load store instruction for normal programs. So, that is why if you have 2 kind of network layer and not network, 2 actually NOCs, one is just for normal load store, another is just for cache coherence or any other related messages, those are needed, but not functional, then that this overhead. This particular example we kind of thought, okay, how about we use a similar philosophy, and whichever extra NOC we have we can use, but again this is orthogonal to the discussion of do we do it in the single NOC in time multiplex manner, or we actually have 2 physical NOCs. From a user perspective, it's you do not need to know this, whether there is 1 or 2, you do not need, you just program it and it is going to work. So, we kind of pause it now for the tea break, we will start at 4 o'clock. Thank you. Good afternoon. In the previous lecture, we talked about how do we use machine learning to perform denial of service attack detection. Now, we are going to look at how do we try to find or detect another attack like eavesdropping attack. And as you will realize, although the attack is different, the whole machine learning story is pretty identical. So, what is eavesdropping attack again? In eavesdropping attack, a sender sending a packet to a destination D, and in between another attacker is sitting, and attacker is able to kind of sniff or get the packet. That is basically the idea. So, that is the eavesdropping. So, you want to figure out whether the eavesdropping going on. Now, if the attacker is sniffing only 1 or 2 packets, it is very difficult to figure out for anybody. But if it is sniffing a lot of packets in a certain time, then by looking at the traffic in certain kind of area, you might be able to make a thing. So, there are different kind of detection and analysis technique, but the key idea is the existing ones are for very highly predictable scenarios. So, machine learning will be able to kind of consider variations, and this story is kind of same thing. So, you kind of have a attacker somewhere that is trying to do an attack or listen to somebody, and it could be implemented through some form of Trojan and some node, and then it kind of work together. Now, it is not just that it can copy packets. So, copying is basically the payload here for the Trojan, but after it copy, it sends it to somebody, another node. So, think about it is copying it here, and then it might give it to the another node where a program is running, and they together collaboratively kind of may do the attack. So, as you will see, the kind of whole idea is you want to do feature engineering of the NOC traffic, then you want to collect kind of the data, and so during this kind of training time, you kind of have those kind of stories. So, model they do the training, and then you have those training done, then during runtime you still do data collection during runtime, and wherever you are making the decision, wherever you installed your machine learning unit, and then you kind of infer is it a eavesdropping attack going on or not. So, here is the detailed algorithm eavesdropping sensing, but key idea basically is that when you kind of look at somebody trying to communicate from 1 to so from 0 to basically 15, at that point the attacker in the middle is kind of sitting here listening and then trying to kind of send to different nodes for kind of processing. And this diagram that you have seen, it may look exactly the same, because it is doing exactly same thing. You collect the log or the traffic traces in the NOC, do kind of different type of feature generation, then you kind of figure out redundant feature you remove, initial model training, then you do model validation, choose which features are good, then finally you kind of do the testing to figure out do I have a model that is going to work. And as I said, there are other features that you might want to use, whether in terms of path, position and all that might be useful. This all of this we kind of have looked at. So, in terms of results, how well does it work, that depends on how much of eavesdropper, how much of data the eavesdropping is going to consume. We still have similar kind of configuration that in a normal in node 0 and node 15, normal one is working on, and attack is going on node 2 and node 14, right. So, for example, node 2 here and node 14 here, they collectively work together. So, they are working, and as you can see the train configurations, whatever attack, and the test configurations, they have no similarity, they are totally different. And in terms of the different performance kind of, if you look at for the regression, multi-layer perceptron, decision tree, random forest, as you will see even the previous one XG boost was kind of doing better, this is also doing better in this particular case. And this particular was when 50% of the data is sniffed by the eavesdropper. If eavesdropper is, and this prediction accuracy, no matter which model you take, let me see if I have the result. Yes, I do. So, basically when you have the amount of data that is getting sniffed, if you look at when you have kind of, this is the training one, right. So, when you have about 50% data, you are looking at somewhere around 80-85% validation. When somebody is sniffing 100% of the data, even then you are looking at somewhere less than 95%. But if you consider 25 or 10% of the data, then your prediction accuracy is low, very close to random guess. So, less and less data the eavesdropper consumes using a standard machine learning techniques like this would not work. So, if you want to publish a paper in this area, what you have to establish that you can build a model, machine learning model, that is going to consume 10% of the eavesdropping scenario, and it can still do a wonderful prediction, not 60%, maybe 70-80%. If you just get those results, that is not publishable. You have to have an intuition why machine learning or which type of machine learning model, how did it figure out with such a little data. Because what it's figuring out is, remember, extra traffic, extra conjunction, extra pattern manually when we are doing, I wanted to show you, that is what machine learning tool is trying to figure out. It is trying to figure out the normal pattern versus abnormal pattern, that is what it is. Any questions? So, for different kind of then the scenario and different traffic kind of story, as you will see the accuracy kind of the EC1, EC2, EC3 different scenarios, it depend on the scenario, but you are looking at kind of different kind of number in the accuracy. That is pretty much what we normally care. We also should care about these numbers, and these numbers are not small either. False positive is actually pretty deadly, false negative is different, but false positive is pretty deadly. You are basically saying the attack is going on, but when it is actually not going on, and that is 23, 19 or 2% of the time. So, now that we kind of talked about different types of attacks and your detection in machine learning, the last one I want to talk about how do you use machine learning to make attack on the NOC itself. This time machine learning is the adversary, earlier machine learning is the friend who is going to tell you something going wrong. So, I want to show you examples of two scenarios, but there are many such scenarios we can discuss. First scenario is traffic analysis attack, second one is breaking anonymity. So, if you recall, we kind of talked about different type of fabric, one is electrical fabric, another is optical fabric, and then we also talked about this kind of wireless fabric, right. So, in case of this wireless fabric, each node is, so this is a 4x4 16 configurations, each of them has a wireless router, and the assumption is anybody wants to talk to anybody, it is a one hop connection. So, if you are thinking in electrical terms, it is point to point communication, as if everybody is kind of. So, if I wanted to create, instead of 16x16, if I want to create a 2x2, it would be connection like this in an electrical domain. Anybody you can reach with one hop, and because everybody has communicating tower, so they would be able to talk to each other, right. So, in this particular example, we call these as wireless hub, and this is the one which is transmitting right now, and this is the malicious one which will try to do whatever it is. And so, what you are looking at here is then this wireless kind of communication, you have time division multiple access based medium. So, this is also called MAC, but it is not message authentication code. This is basically medium access protocol, medium access control that is used for doing this communication, and this is very common known as TMAC, TDMA MAC, that is basically kind of used for wireless communication. And for this wireless NOC, what you are seeing a timestamp, this is timestamp 0, or think of clock cycle 1, this is clock cycle 2 picture, this is clock cycle 15 picture, and different people are, the story is different people are talking at different time. And remember, this is time division multiplexing. If everybody starts talking, assuming the RF bandwidth is for one person to talk, then everybody starts talking or multiple people start talking at the same time, then it is going to be serious interference problem in wireless communication. So, therefore, similar to the story of if you have a bus, similar to the story of if you have a processor 1 talking to processor 2, and if the bus is 32 bit, two people cannot put the request the 32 bit instruction, 32 bit data at the same time. Two people cannot do that, only one can do at a time, because if two people try doing it, somebody wrote 0, somebody wrote 5, you do not know what value will come out of it. It does not have to be even 32 bit, it can be just 1 bit line. If one person is writing 0, another person is writing 1, and you ask what is the result in that, it is non deterministic. In hardware community you call it tri-state. But whatever it is, that basically means these two people, the bus will not allow these two people to write at the same time based on bus arbitration or whatever protocol. Similarly, in wireless community, this TDMA kind of protocol, that basically, so TDMA kind of protocol would basically block you from communicating at that time, whether they are selected based on priority or other, that is beyond the discussion at this point. But it is clear that you are taking a camera and looking at a snapshot what is happening here. But what is important here is the malicious router can kind of snip at every time slot. Whoever is talking does not matter, they can snip and listen, because it is all one hop, and that information is in the air. The idea of one hop is when this person is broadcasting, technically anybody can hear, anybody can hear. Now, in reality, that the story that you have seen here, this is kind of theoretical. It is the designing, implementing, making sure there is no interference when they are sitting so close in millimeter square range. You are putting 16 antenna, just 2 millimeter or 4 millimeter square range. That's not kind of effective. So, then most of the time storage would be similar to this, which is you will have full electrical connectivity, at the same time you will have few towers. So, therefore, if you are trying to communicate from some point to some point, let us mark this the first one as, we can randomly choose this one as a source, and maybe we make this one as destination. Then there are multiple ways. So, probably the closest way would be to kind of going from here to here one hop, then use this wireless connection to here and then to here. There are other possibilities, but this is probably the shortest one, right. So, that is the communication in a hybrid one. Oh, so one thing I forgot to tell you is that here the TMAC token is circulated in round robin manner. Which one would get the chance to pass the data, because this person might say please send mine. So, everybody will kind of might have some request pending, but who will get the chance in this one, it is basically round robin manner. Right now this one has token, so this will transmit, maybe next time later based on the protocol, here is a circular, next time step this one will circulate, this particular token will come here, next time step it will come here, next time step it will come here, and then it will just rotate. So, that is basically the protocol, time division multiplexing protocol for just 4 wireless hubs. And because of that, it should be obvious to you if I just plot it. So, this one is for first Fourier transform, these are again real benchmark from splash benchmark, and this one is FMM, 2 benchmarks. And if you look at it, whether and these are there are 2 hubs, no 4 wireless hubs, and 2 of the benchmarks running, and if you look at it, if you kind of draw a vertical line, you will kind of figure out they are not kind of crossing each other, it is just different kind of time step. When they are communicating, they are kind of communicating in kind of different time steps. So, based on the token and what not, and ideally even this one is not supposed to align with this. This line also not supposed to align with this, even for second benchmark if they are running simultaneously. If not, then it does not matter, but this is basically time slot occupancy, how whenever a wireless hub is getting chance to communicate the data with another wireless one. So, basically TDMA you are looking at. So, like in normal world, non wireless world, when you have a program, the kind of characteristics you look at different programs are different. Similarly, in this wireless communication world or network on chip network world, when you look at data packet and control packet. So, data packet is the data values. So, when you have a packet, right. So, if you wrote an email that got divided into multiple parts and each of the part is taken into a packet, that would have header and MAC and actual data in the message itself and so on and so forth, and whether this arrived or whether this is second one, request, acknowledgement, all of that. So, when message is involved, those are called as data packet. When any of the information of retry, if you are retrying, if it did not come in, or the acknowledgement or any other stuff, that is known as control packet. Ideally control packets are smaller, data packets are larger, but for the simplicity of implementation most academicians make them same size, but whichever way it is, if you look at different benchmark, the amount of control packet data packets are different, right. So, closest analogy in programming language would be you have data path and finite state machine, or you have number of if statement or for statement versus regular assignment statements. So, this is similar to in terms of packet, there are typically more control packets than data packets. So, what is the threat model in this particular kind of scenario? So, basically the threat model goes like this, that you have this 4 cross 4 kind of story and then you have multiple one, and one of the maybe this wireless hub has the capability of kind of in that their protocol TDMA MAC protocol, there are some kind of Trojan or some kind of malicious implant, and what they are able to do, they are able to sniff the data and then send it to an outside node. It could have been one of the inside node where it has kind of some neural network to do some kind of analysis. So, this is typically known as colluding application. Now, it is quite possible that application also sitting in that same node, it does not have to be in another node, but it could be in another node, another place. Remember, it has a wireless the communication capability. So, it has much better leverage or power, attack power than somebody with electrical connectivity. So, in detail how does it work? Basically then you have some Trojan or malicious implant that is extracting some of the information and then extract the TMAC traffic trace. So, from the traces, then it kind of based on certain observation what something is happening or a trigger condition, it is going to activate the HT and pre-process and combine traffic traces and then deactivate the HT, because if it keeps itself activated, everybody else is listening. So, they might be able to figure out. So, then get the traces and then kind of send the traces to another adversarial node who will basically infer it, and the wherever you are sending, if you are an attacker, you already pre-trained the model for your attack and then you are basically making use of it. So, how well does it work, how much it is able to attack, or so what it is basically in this particular example what is trying to figure out is what program is running there, right. So, what program is running there, that is what it is trying to figure out, or who is talking to whom, whatever it is trying to figure out, the basically accuracy is pretty kind of high with 2 layer CNN, and if you go for 4 layer CNN, now this CNN neural network is the attacker's neural network, not yours or mine. So, this basically the accuracy is very high, with high accuracy you can figure out what is going on in the victim node with reasonably high accuracy. Even with a 4 layer CNN you can get close to for certain topologies. I believe one of them is mesh, another is Toro and all that. So, certain topologies it is even with 100% accuracy you can figure out what is going on. So, this attack is very kind of powerful, and there are certain defenses also. I am going to skip those. So, now I am going to talk about the last attack, which is actually simple to explain and which is called flow correlation attack. So, the key idea is when two people are talking, and even if it is kind of encrypted data, how do you figure out who is talking to whom, right. And so, because whenever there are kind of the idea of many of the time people kind of do this what is it called you kind of do onion routing, right. We talked about you do onion routing and anonymous routing, and many of time in the computer networks the idea is all of these, the whole network itself is anonymous, anonymity is preserved here, but anonymity is not preserved at the source and at the destination. So, if it is not preserved, then somebody might be able to do somebody might be able to figure out by looking at what is going on here. If this is, think about this is unencrypted and this is unencrypted, then you can figure out. Of course, how they will talk, that is different, and in fact, any of the network like Tor network, that is completely anonym, gives you guarantee of anonymity, but when the communication enters the Tor network or when it exists the Tor network, if two computer can sit there and analyze the traffic pattern, assuming other people are not talking at that time, then it will be able to figure out who is talking to whom, because everybody's talking pattern is different. How frequently I call Professor Sahu, if somebody is observing that kind of number or pattern, then you know who is talking to whom. So, that is basically the key idea here, and the way basically attack happens, that you do training time, you kind of do the data collection, you train the attacker DNN, and then here during attacking time you are basically potentially communicating pair, you are coming and predicting correlation, and you are basically breaking the anonymity. So, if you are thinking from a machine learning perspective, during training time machine learning kind of figured out all these combinations. It figured out if R1 is talking to R11, how the pattern would be, if R1 is talking to R9, how the pattern would be, R5 is talking to R15, what the pattern would be. So, it kind of figured out. Now, when R1 talking to R15, it really does not say much. What R1 is running, that is important. There is also something important, because the thing is, when remember the number of control packet, data packet that I have shown, how much and how many, and the frequency. If you recall, we talked about for loops and cache accesses, cache misses. Depending on the computation or depending on the messages, the frequency, interpacket delay, all of that has important correlation, right. And if every day you call your mother at the morning or evening, if there is a call coming to your mother, then neighbors will know it is coming from you. Assumption is nobody else calls you that time, right. So, whether it is the time of arrival or whether the frequency of arrival, that uniquely identifies everybody's unique characteristics. If everybody decides to call their mother at random time, of course, neighbor will not be able to figure out, and in fact, that is one of the mitigation here. Any question? Is the key idea clear, that even if you make completely wrap this with a secure envelope, secure entourage, if somebody has a listener here, somebody has a listener here, and all they are observing kind of the pattern of arrival, pattern of call, think about it, pattern of messages and their distance between them, frequency arrival, how many coming within what duration, and somebody is observing here and they talk to each other, then it is completely broken. Anything in between completely secure. So, these are all secure channel, like you can think of virtual private network or any other mechanism. So, the key ideas I kind of trying to pictorially illustrate. So, interfleet delay. So, what are these fleets? Think of packets or smaller fragment of the packet, and what kind of delay it kind of demonstrate. So, once you have that piece of information, then so once you have that kind of information, you just basically match whether this information here is actually same as here. In this picture, I intentionally interfleet delay at the source, and this I basically just photocopied. Interfleet delay at destination is same, then you kind of know that is what it is. And effectively the attacker is trying to do the same thing wherever it is sitting, the based on that. But this is assumption basically relies on the fact during training time the attacker is able to know who is talking and what frequency they are, what application running, how their pattern is, and the machine learning model is trained. And if you look at the kind of results, then you will see that for different kind of mesh sizes, whether 4 cross 4, 8 cross 8, 16 cross 16, you will see the accuracy is reasonably high using the idea of interfleet delay or flow correlation attack. Any questions? If you have no questions, that is where we end today. We will see all of you tomorrow at 10 o'clock. Thank you. Come prepared for the exam. We will have exam immediately after the lunch. And we have lunch here, right? We have lunch here, right? Yes. And it is biryani? Everybody is smiling. So exam made people unhappy, then biryani. If you said preference of non-veg, make sure you take the non-veg biryani. If you said veg, then take the veg. Otherwise, you will be in deep trouble. We ordered only 10. 9 of you said vegetarian. We ordered only 10 veg biryani. Don't take the veg just for the heck of it too much. I think it's a big biryani. Is that a problem? That's okay. We save 1 meal.